Look up at the night sky. It feels timeless, doesn't it? A serene, silent canvas dotted with stars that seem fixed and eternal. But what if I told you that this peaceful scene is an illusion? That behind that stillness lies one of the most explosive and puzzling truths science has ever uncovered. The universe isn't just expanding, it's accelerating, stretching itself apart faster and faster with every passing moment. And the force behind this great cosmic speed-up is something we can't see, can't touch, and barely understand. It's called dark energy, and it makes up more than 2/3 of everything in existence. Yet, it hides in plain sight, shaping the fate of the cosmos while remaining utterly invisible to us. This isn't some abstract idea discussed only in university classrooms or advanced research papers. It's a mystery that touches the very nature of reality itself. Why is the expansion speeding up? What is this mysterious dark energy that seems to defy gravity and push galaxies apart? And what does it mean for the future of everything, our solar system, our galaxy, and even the atoms that make us who we are? These aren't just questions for astronomers. They're deeply human questions about where we came from, where we're headed, and how the story of the universe will ultimately unfold. In this video, we're going to embark on a journey to decode dark energy. We'll travel back in time to explore what Einstein once called his biggest blunder, an idea he discarded, only for it to resurface decades later as perhaps his most stunning insight. We'll relive the moment researchers first saw the evidence for acceleration in the light of dying stars, a discovery so shocking it turned cosmology upside down and earned a Nobel Prize. And we'll dive into the mind-bending theories scientists are exploring today, from ghostly energy fields that shift over time to radical revisions of gravity itself. By the end, you won't just understand what dark energy is, you'll feel the awe and curiosity driving the scientists who are racing to solve this puzzle. You'll look up at the stars not as distant, static points of light, but as part of a living, breathing, and ever-growing cosmic tapestry, one whose full story we are only just beginning to read. It all started with a single number, a tiny, seemingly insignificant term tucked into the most famous equations ever written. In 1915, Albert Einstein unveiled his theory of general relativity, a revolutionary new description of gravity that portrayed the cosmos not as a static stage, but as a dynamic, malleable fabric that could bend, warp, and even evolve. But when Einstein applied his equations to the entire universe, he ran into a problem. The gravity of all the matter he knew existed should have been causing the universe to collapse in on itself. This didn't sit right with him because, like most scientists of his day, he believed the cosmos was eternal and unchanging, so he made a small adjustment. He introduced a fudge factor, a mathematical counterbalance to gravity. He called it the Cosmological Constant, represented by the Greek letter lambda. This constant was a repulsive force, woven into the very fabric of space itself, that would push outward just enough to perfectly counteract the inward pull of gravity, holding the universe in a perfect, steady state. It was an elegant solution, but it was born from a desire for stability rather than from any observational evidence. Then, in the 1920s, along came Edwin Hubble. Using the most powerful telescope of the era at Mount Wilson Observatory, Hubble made a staggering discovery. By observing distant galaxies, he found that they were all moving away from us, and the farther away a galaxy was, the faster it was receding. The universe wasn't static at all, it was expanding. Einstein's equations, in their original form without the constant, had actually predicted this possibility, but he had dismissed it. Upon hearing Hubble's confirmation, Einstein reportedly declared that introducing the cosmological constant was the biggest blunder of his entire career. He had missed a chance to make one of the greatest predictions in the history of science, and so the constant was scrubbed from the textbooks, a discarded idea from a bygone era. For decades, that's where the story ended. The cosmological constant was a curious footnote, a reminder that even the greatest minds can be led astray by their own assumptions. The expanding universe became the standard model, with scientists debating whether it would expand forever or eventually slow down and collapse back in a big crunch. But the universe, it seems, has a profound sense of irony. In the late 1990s, two independent teams of astronomers were using the Hubble Space Telescope, named, of course, for the man who had proven Einstein wrong, to study distant supernova. They were trying to measure how much the universe's expansion was slowing down due to gravity. Instead, they found the exact opposite. The expansion wasn't slowing down, it was speeding up. Something was pushing galaxies apart with ever-increasing force. Cosmologists were stunned. They needed an explanation, and they found it waiting for them in the pages of history. They reached back and dusted off Einstein's forgotten idea, his so-called blunder. The cosmological constant was suddenly resurrected, not as a mechanism for a static universe, but as the very engine of an accelerating one. That repulsive force inherent to the vacuum of space was exactly what was needed to explain the new observations. In a breathtaking twist, Einstein's greatest mistake was transformed into his most prescient insight, a concept decades ahead of its time. This story is a powerful lesson in how science really works. It's not a straight line from question to answer. It's a winding path filled with wrong turns, discarded ideas, and brilliant blunders that later reveal their brilliance. It shows that our understanding of the cosmos is always evolving, and that sometimes the key to unlocking the future is hidden in the puzzles of the past. With the cosmological constant back on the table, the race was on to find the hard evidence that would prove this acceleration was real. So how do you measure the acceleration of the entire universe? You need a cosmic speedometer, a way to gauge vast distances with incredible precision. For the two teams racing to answer this question in the 1990s, that tool was a very specific kind of stellar explosion, the Type 1, a supernova. Think of these events as the universe's pre-calibrated light bulbs. A Type 1, a supernova, occurs in a binary star system where a dense white dwarf siphons material from its companion. Once it reaches a critical mass, a very specific threshold known as the Chandrasekhar limit, it undergoes a runaway thermonuclear explosion. Because this detonation always happens at the same mass, the peak brightness is always virtually identical. This makes them perfect standard candles. If you know how bright something truly is, you can measure how bright it appears from Earth and precisely calculate its distance. It's like seeing a familiar 100-watt light bulb from far away. The dimmer it looks, the farther away you know it must be. The two teams, the Supernova Cosmology Project led by Saul Perlmutter, and the High Z Supernova Search Team led by Brian Schmidt and Adam Rees, embarked on a monumental task. They weren't just looking for any supernova, they were hunting for the most distant ones they could find, billions of light years away. To see back in time is to look out into deep space, and these ancient stellar explosions would allow them to effectively measure the expansion rate of the universe at different epochs in its history. The process was painstaking. They would point the world's most powerful telescopes, like the Keck Observatory in Hawaii and the Hubble Space Telescope, at a patch of sky to take a picture. Then, weeks later, they would take another image of the exact same patch and meticulously comb through the data, pixel by pixel, searching for a new pinprick of light that wasn't there before, the telltale sign of a supernova igniting in the void. The goal was to see how much the expansion of the universe had slowed down over billions of years due to the relentless pull of gravity. The expectation was unanimous. The gravity of all the matter in the cosmos was acting like a brake, so the expansion should have been decelerating. The more distant supernova, which exploded longer ago, should have shown a specific relationship between their distance and their redshift, a measure of how much the universe had stretched since the light left the star. But the data told a completely different story. The incredibly distant, ancient supernova weren't just far away, they were too far away. They appeared fainter than anyone had predicted. After checking and rechecking for errors accounting for interstellar dust, potential miscalibrations, and every conceivable astronomical confounding factor, the shocking conclusion became inescapable. The supernova were dim because they were farther away than the standard model of a decelerating universe could explain. The only possible reason was that the expansion of the universe wasn't slowing down at all. It was speeding up. Imagine the sheer disbelief in those rooms. Adam Rees described the moment as a feeling of terror, worrying that they had made some colossal, embarrassing mistake. Brian Schmidt recalled thinking the result was so nuts that he spent the next 2 weeks trying to kill it, to find the error that had to be there. Saul Perlmutter's team, arriving at the same startling conclusion independently, went through the same gut-wrenching process of doubt and verification. But the evidence was robust, it was consistent, and it was real. In 1998, they announced their findings to the world, and cosmology was turned on its head. The universe was being pushed apart by a mysterious, repulsive force. This wasn't a minor adjustment, it was a fundamental rewriting of the cosmic story. For this breathtaking discovery, Perlmutter, Schmidt, and Rees were awarded the 2011 Nobel Prize in Physics. This was the moment dark energy was forced onto the stage. The meticulous, patient work of these astronomers comparing the faint light of ancient dying stars across billions of years had unveiled a truth more profound and strange than anyone had dared to imagine. It was a stunning testament to the scientific method. You follow the evidence wherever it leads, even if it leads to a place that completely defies your expectations. The acceleration was the clue. The dimness of those supernova was the fingerprint of something invisible at work. Now, the pressing question shifted from if the universe was accelerating to why. What unseen force could possibly be strong enough to overcome gravity and drive the entire cosmos apart faster and faster? The hunt for the identity of this mysterious agent was officially on. So we have this incredible Nobel Prize-winning discovery. The universe is accelerating, but what is actually causing it? Scientists gave this mysterious something a name: dark energy. It's a label for our ignorance, a placeholder for whatever it is that's stretching the very fabric of the cosmos at an ever-increasing rate. To understand it, we first need to appreciate how it's the complete opposite of everything we're familiar with. Think about gravity. It's a force that pulls things together. It's what keeps your feet on the ground, our planet orbiting the sun, and our galaxy held together. Gravity is an attractive force, and on the largest scales, we would expect it to be slowing down the expansion of the universe, acting as a cosmic brake pedal. Dark energy, however, is like a cosmic accelerator pedal. It's a repulsive force that pushes things apart. It doesn't pull galaxies together. It pushes the space between them, making the entire universe expand faster and faster. What are the properties of this bizarre component? First, we know it's incredibly smooth. It permeates all of space uniformly and evenly. Unlike matter, which clumps together into stars, planets, and galaxies, dark energy appears to be the same everywhere. A cubic meter of space here in our solar system has the exact same amount of dark energy as a cubic meter of space in the deepest, emptiest void between galactic superclusters. This uniform distribution is a key clue. Second, and this is perhaps the strangest part, it has a powerful negative pressure. In our everyday world, we're used to positive pressure. If you squeeze a balloon, the air inside pushes back. That's positive pressure. Negative pressure is different. It's more like a tension. Imagine stretching a rubber band. The tension you feel as you pull is a form of negative pressure. Now, apply that idea to the fabric of space itself. According to Einstein's theory of general relativity, something with a strong enough negative pressure can generate a repulsive gravitational effect. This isn't science fiction. It's embedded in the mathematics of how gravity works. So dark energy isn't some magical anti-gravity beam shooting through the cosmos. It's a property of space, an inherent tension or energy that causes gravity itself to act in reverse on the largest scales, making the universe push itself apart. This leads us to the standard model of our universe, known to cosmologists as the lambda CDM model. This isn't just a random jumble of letters, it's a precise recipe for the entire cosmos. Lambda represents the cosmological constant, which is the simplest mathematical description for dark energy. CDM stands for cold dark matter. The model tells us that the universe we can see, all the stars, galaxies, gas, and planets, makes up less than 5% of the total content of the cosmos. About 27% is dark matter, the invisible scaffolding that holds galaxies together with its gravity, and a staggering 68% is dark energy, the dominant component that controls the ultimate fate of the expansion. The name dark is used for both dark matter and dark energy, but for very different reasons. Dark matter is dark because it doesn't interact with light. It doesn't emit, absorb, or reflect it, so we can only detect it through its gravitational pull. Dark energy is dark for an even more profound reason. It doesn't seem to interact with anything in any way we can directly detect. It doesn't clump, it doesn't scatter particles, and it doesn't decay. It simply is. It's a smooth, uniform energy infused into the vacuum of space itself. This is a crucial point to grasp. We often talk about dark energy as if it's a substance, a thing, a type of particle flowing through the cosmos. But based on everything we currently know, that's probably the wrong way to think about it. It's not a ghostly fluid or a sea of invisible particles. It appears to be a fundamental property of empty space. The vacuum of space isn't truly empty. Quantum physics tells us it's a seething, bubbling foam of virtual particles popping in and out of existence. This vacuum has an energy, and that energy, according to this idea, has the exact negative pressure needed to drive the acceleration. So when we say the universe is expanding, it's more accurate to say that space itself is being created. And with that new space comes more of this innate dark energy, leading to more push, which creates more space in a runaway feedback loop that is accelerating the expansion. We are left with a profound and humbling realization. The force that determines the destiny of our entire universe isn't some exotic material from a distant place. It's an enigmatic energy intrinsic to the nothingness all around us, a secret hidden in the void. So with dark energy identified as the culprit behind the acceleration, the most straightforward explanation was waiting in the archives of physics, a ghost from Einstein's past. The cosmological constant, that little lambda he added to his equations and then famously discarded, was suddenly the perfect candidate. In this model, dark energy isn't a strange new substance or a dynamic force. It's simply a property of empty space itself. The vacuum isn't truly empty. Quantum physics tells us it's a seething, bubbling foam of virtual particles flickering in and out of existence. This vacuum has a fundamental energy density, and the cosmological constant is the idea that this energy is an immutable, unchanging feature of the cosmos. It's a constant energy infused into every single cubic centimeter of space, and as the universe expands and more space is created, the total amount of this vacuum energy increases, driving the expansion faster and faster. The beauty of this idea is its profound simplicity and its deep roots in established physics. It doesn't require inventing any new particles or forces. We already have the mathematical framework for it in Einstein's general relativity. We just have to set that constant to a value other than zero. It's the most economical solution, the one that makes the fewest assumptions. In many ways, it's the Occam's razor choice for dark energy. The cosmological constant provides a wonderfully elegant fit to a vast array of observational data, from the supernova measurements to the patterns in the cosmic microwave background and the large-scale structure of the universe. When you plug lambda into the equations, it works spectacularly well at describing the universe we see. But this elegant solution comes with a colossal, almost embarrassing problem. When physicists try to calculate what the value of this vacuum energy should be based on our best theories of quantum mechanics, they arrive at a number that is utterly, catastrophically wrong. They add up all the possible contributions from all the quantum fields that permeate the vacuum, and the result is a number that is 10 to the power of 120 times larger than the value we actually observe from cosmological measurements. That's a 1 followed by 120 zeros. This isn't just a small error, it's the single worst prediction in the entire history of science. To say the predicted value and the observed value are not in the same ballpark is a gross understatement. It's as if theory predicted the entire observable universe should be made of energy, while observation tells us the actual value is barely a single drop of water. This is known as the cosmological constant problem, and it represents a fundamental chasm between our understanding of the very large general relativity and the very small quantum mechanics. This staggering discrepancy suggests one of two things. Either our method for calculating the energy of the vacuum is deeply flawed in a way we don't yet understand, or some mysterious, precise cancellation mechanism is at work, perfectly neutralizing almost all of that enormous quantum energy to leave behind the tiny, yet cosmologically significant, amount we detect. This problem is so severe that it leads many physicists to suspect that the cosmological constant, for all its elegant appeal, might be an incomplete answer. It fits the data, but it points toward a profound gap in our fundamental knowledge. The ghost of Einstein's idea is both the simplest solution and a constant reminder of how much we have yet to learn, pushing scientists to look beyond this constant vacuum energy and consider the possibility that dark energy might not be constant at all. Frustrated by the staggering fine-tuning problem of the cosmological constant, many theorists began to explore a far more dynamic and exotic possibility. What if dark energy isn't a fixed property of the vacuum, but something that changes and evolves? This idea has a beautiful, almost mythical name: quintessence. In ancient philosophy, quintessence was the fifth element, the pure and perfect substance that made up the heavens, beyond the earthly elements of air, fire, water, and earth. In modern cosmology, it represents a fifth fundamental force, a new kind of field that permeates all of space but, unlike Einstein's constant, is very much alive and active. Think of quintessence not as a static number in an equation, but as a kind of cosmic weather system, an energy field that can vary in its intensity over time and even across space. It's what physicists call a scalar field, meaning it has a value but no direction, much like the temperature in a room, a value that can be higher or lower at different points. In the very early universe, this field might have been dormant or weak, allowing gravity to dominate and pull matter together to form galaxies. But as the cosmos expanded and diluted, the energy density of this field could have slowly become more significant, eventually taking over and starting to push the expansion faster. This dynamic nature is the crucial difference. The cosmological constant is like a painting, fixed and unchanging once the universe began. Quintessence is more like a movie, a rolling narrative where the strength and influence of dark energy can change as the plot of the cosmos unfolds. This flexibility makes quintessence an incredibly attractive idea for solving some of the Lambda model's biggest puzzles. The most famous is the "why now?" problem, or the cosmic coincidence. We appear to live at a very special moment in cosmic history, just as dark energy is beginning to dominate over matter. If dark energy were a true constant, this is just a bizarre and unexplained bit of timing. But if it's a dynamic field, its rise to power could be a natural consequence of its evolution, a chapter in a much longer story that doesn't require us to be living at a uniquely privileged instant. Furthermore, the unfathomable fine-tuning problem, the one with the 120 orders of magnitude, might be alleviated. With a dynamic field, the value we measure today isn't a fundamental constant set at the beginning of time. It's simply the current reading on a cosmic dial that has been slowly turning for billions of years. It could have started with any value and naturally evolved to what we see now, making its seemingly precise and tiny value far less mysterious. This evolving nature of quintessence opens up a breathtaking range of possible futures for our universe, far beyond the steady expansion forecast by the cosmological constant. The fate of everything hinges on the equation of state parameter, which for quintessence isn't fixed at -1. If the field evolves in a certain way, it could weaken over time, perhaps eventually fading away and allowing gravity to once again slow the expansion, though likely not enough to cause a big crunch. Or it could do the opposite, it could strengthen. In this most dramatic scenario, the repulsive force of quintessence grows without bound, becoming infinitely powerful. This would lead to a truly apocalyptic end known as the Big Rip. First, galaxy clusters would be torn apart, then individual galaxies. As the acceleration becomes overwhelming, solar systems are ripped to shreds. In the final moments, stars and planets are vaporized, and in the last fraction of a second, the very atoms and subatomic particles that make up all matter are torn apart by the expansion of space itself, ending the universe in a silent, terrifying flash of nothingness. Of course, quintessence is still entirely theoretical. No one has directly detected such a field, and current observations from supernova and the cosmic microwave background still agree very well with a simple cosmological constant. But the beauty of quintessence is that it offers a rich, testable alternative. It makes specific predictions about how the expansion rate should have changed over the universe's history in subtle ways that differ from a pure lambda model. The hunt is now on for those tiny deviations. The next generation of telescopes like the Vera C, Rubin Observatory and the Nancy Grace Roman Space Telescope are designed to be so exquisitely precise that they could potentially measure the fingerprints of a dynamic dark energy field, watching for any sign that this fifth force is real and changing among the distant galaxies. So we have these two compelling but competing theoretical ideas: the steady, unchanging cosmological constant and the dynamic, evolving field of quintessence. How do we move beyond theory and actually test which one, if either, is correct? We can't put dark energy in a lab jar or point a telescope directly at it. Instead, cosmologists have become cosmic detectives, using the universe itself as their laboratory and developing incredibly clever tools to measure the indirect effects of this mysterious force. This isn't a single-pronged approach. It's a full-scale, multi-front investigation where 4 powerful and independent techniques are used to cross-check and verify each other's results. The goal is to build an ironclad empirical case for the nature of dark energy by measuring how the expansion rate of the universe has changed over billions of years. The first tool, the one that started it all, is the use of Type 1, a supernova. We already know how this revolutionary method works. These supernovae act as standard candles, their known brightness allowing us to measure vast distances across space and time. By comparing the distance of a supernova to its redshift, a measure of how much its light has been stretched by the expansion of the universe, astronomers can reconstruct the expansion history. If the universe's expansion is accelerating, the distant supernova will appear fainter than expected. This technique directly revealed the acceleration, but to confirm it and probe deeper, we need more lines of evidence. That's where the other probes come in, each providing a completely different way to measure the cosmos's growth. The second powerful technique involves listening to the faint echoes of the early universe, a fossilized sound wave known as baryon acoustic oscillations, or BAO. To understand this, we need to travel back to the universe's infancy, just a few 100,000 years after the Big Bang. At this time, the cosmos was a searingly hot, dense plasma of particles and light. In this primordial soup, gravity was trying to pull matter together into clumps, but the intense pressure of the radiation was pushing it back out, creating a series of rhythmic pressure waves that sloshed through the plasma, much like sound waves moving through air. When the universe finally cooled enough for atoms to form in an event called recombination, the light was set free, creating the cosmic microwave background. But at that moment, those sound waves were suddenly frozen in place, imprinting a preferred scale on the distribution of matter, a specific distance that those waves had managed to travel before the universe became transparent. This distance, about 500 million light-years across, became a permanent cosmic ruler etched into the fabric of the universe. As the universe expanded, this ruler stretched along with it. Today, we can see the imprint of this ruler in the large-scale structure of the cosmos. When we create immense 3-dimensional maps of millions of galaxies, we don't see them scattered randomly. We find that they are statistically more likely to be separated by this specific, scaled-up distance than any other. It's like finding a vast, invisible grid underlying the distribution of galaxies. By measuring the apparent size of this standard ruler at different epochs in cosmic history, we can measure how the universe has expanded between then and now with extraordinary precision. BAO doesn't rely on the brightness of objects, so it's immune to many of the systematic errors that can plague supernova studies. It provides a robust, geometric measurement of expansion that powerfully corroborates the supernova results. The third probe takes advantage of one of Einstein's most dramatic predictions, that gravity can bend the very path of light itself. This is called gravitational lensing. On a large scale, we use a subtle version known as weak gravitational lensing. As light from incredibly distant galaxies travels across billions of light-years to reach our telescopes, it passes through the cosmic web of dark matter and dark energy. The gravitational pull of all this matter, both visible and dark, very slightly distorts the shapes of those background galaxies, stretching them from perfect circles into tiny, coherent ellipses. It's an effect so minuscule you can't see it with any single galaxy. It requires statistical analysis of the shapes of millions of galaxies to detect the subtle pattern of distortion. By mapping this cosmic shear across the sky, astronomers can effectively create a mass map of the universe. they can see how matter, both dark and normal, is clustered. But crucially, this clustering is influenced by the expansion history governed by dark energy. The faster the expansion accelerates, the more it suppresses the growth of these large-scale structures over time. Weak lensing allows us to measure the growth of structure throughout cosmic history. By comparing this growth to the expansion history measured by supernova and BAO, we get a critical cross-check. If dark energy is a cosmological constant, the growth of structure should match one specific pattern. If it's something else, like quintessence, it could leave a different fingerprint on how cosmic structures form. This makes weak lensing an indispensable independent test. The fourth and perhaps most foundational pillar is the cosmic microwave background, the CMB. This is the afterglow of the Big Bang, the oldest light in the universe, released when the first atoms formed. While it is a snapshot of the universe at a very young age, it holds profound implications for dark energy billions of years later. The CMB shows tiny, minuscule fluctuations in temperature anisotropies that correspond to regions of slightly different density in the early plasma. The precise patterns of these hot and cold spots tell us a tremendous amount about the composition and geometry of the universe. They tell us the total amount of matter and energy in the cosmos, and that the universe is geometrically flat. This might seem unrelated to dark energy, but it's everything. The CMB gives us the initial conditions of the universe. It tells us how much matter there is to slow down the expansion through gravity. When we combine this with measurements of the expansion rate today, there's a glaring discrepancy. There simply isn't enough matter to account for the fact that the universe is flat. Something else must make up the difference. That something is dark energy. The CMB doesn't measure dark energy's evolution directly, but it pins down its density with incredible accuracy. It tells us that dark energy must constitute about 68% of the universe, a number that aligns perfectly with the other probes. It provides the grand, overarching framework within which all the other measurements make sense. To harness the power of these four techniques, scientists have launched monumental collaborative projects. The Dark Energy Survey, which operated from 2013 to 2019, used a 570-megapixel camera on a telescope in Chile to map hundreds of millions of galaxies, measuring weak lensing, BAO, and the distribution of galaxy clusters in unprecedented detail. Its results have powerfully constrained the properties of dark energy, strongly favoring a cosmological constant, but not yet completely ruling out some forms of quintessence. But this is just the beginning. The baton is now being passed to a new generation of even more ambitious missions. The European Space Agency's Euclid telescope, launched in 2023, is now embarking on a 6-year mission to create a colossal 3-dimensional map of the universe, measuring the shapes and redshifts of over 1 billion galaxies. It will take weak lensing and BAO measurements to a whole new level of precision. Later this decade, NASA's Nancy Grace Roman Space Telescope will join this effort, conducting a giant survey to discover thousands of distant Type 1, a supernova, and map the distribution of millions of galaxies. Its wide field view will give us a breathtakingly detailed movie of cosmic expansion. And on the ground, the Vera C. Rubin Observatory's Legacy Survey of Space and Time will begin a 10-year, all-sky survey that will effectively watch the universe on a massive scale, detecting billions of galaxies and countless supernovae. The combined firepower of these projects represents the largest and most coordinated scientific endeavor in the history of cosmology. They are not working in isolation. They are a symphony of observation, with each instrument playing a different part. By weaving together the threads of data from supernova, sound waves, light bending, and primordial light, we are closing in on the true nature of dark energy, moving from a mystery to a measured phenomenon. But to truly understand dark energy's role from the very beginning, we need to look at the oldest picture we have of the universe, the cosmic microwave background. This isn't just ancient light, it's the very afterglow of the Big Bang itself, a fossilized snapshot of the cosmos when it was a mere 380,000 years old. Before this moment, the universe was an opaque, searingly hot plasma, so dense that light particles, photons, were constantly bouncing off free electrons trapped in a chaotic dance. They couldn't travel in a straight line, but as the universe expanded and cooled, it eventually reached a critical temperature where electrons could combine with protons to form the first neutral atoms. In an instant, the cosmic fog cleared. The photons, suddenly freed, streamed outward across the universe. That first flash of light is what we detect today as the CMB, a nearly uniform curtain of microwave radiation that fills every cubic centimeter of space, a constant reminder of our fiery origins. What makes this ancient light so incredibly valuable to cosmologists isn't its uniformity, but its tiny, exquisite imperfections. When we build exquisitely sensitive instruments to map the CMB, like the Planck satellite, we don't see a perfectly smooth blanket of light. Instead, we see a mottled tapestry of incredibly slight temperature variations, tiny patches that are a few millionths of a degree warmer or cooler than the average. These minuscule fluctuations are anything random. They are the blueprint for everything we see in the universe today. They represent the primordial seeds, the regions of slightly higher and lower density in that early plasma. The slightly denser spots had a little more gravity, and over billions of years, they pulled in more and more matter, eventually growing into the vast cosmic web of galaxies, clusters, and superclusters that we observe now. The patterns in this baby picture hold encoded information about the contents, shape, and ultimate fate of the entire cosmos. This is where the connection to dark energy becomes absolutely critical. The precise size and distribution of these hot and cold spots act as a powerful cosmic divining rod, revealing the total amount of matter and energy in the universe. Think of the patterns of sound waves in that early plasma. They had a characteristic size, a preferred wavelength determined by how far a pressure wave could travel before the universe became transparent. This scale appears in the CMB as a very specific, dominant size for the hot and cold spots. The apparent angular size of these spots on the sky today tells us fundamental truths about the geometry of the universe. The measurements from Planck and other missions show with undeniable certainty that the universe is geometrically flat. This doesn't mean it's like a sheet of paper. It means that parallel lines stay parallel, and the rules of Euclidean geometry we learned in school hold true on the largest scales. But a flat universe presents a profound puzzle. For the universe to be flat, the total density of all matter and energy must be exactly at a critical value. When scientists added up all the matter they could see, stars, galaxies, gas, and all the dark matter inferred from its gravitational pull, they came up dramatically short. There simply wasn't enough stuff to make the universe flat. Something else, something that doesn't clump like matter, had to be making up the difference, about 68% of the entire energy budget of the cosmos. That something is dark energy. The CMB didn't directly observe the accelerated expansion, but it provided the foundational evidence that dark energy must exist, and in what staggering abundance. It gave us the starting conditions. When we combine this pristine snapshot of the infant universe with observations of the adult universe today, like the distances to supernova, the conclusion is inescapable. The universe started with these specific initial conditions, and it has evolved into the accelerating expansion we see now. The only way to make the math work is to include that dominant, smooth, repulsive energy component. The cosmic microwave background is our anchor in time, the fixed point that allows us to measure how much the universe has stretched and changed over 13.8 billion years, confirming that dark energy is the dominant force steering the cosmic expansion. While the cosmic microwave background gives us a pristine baby picture of the universe, it's a single, two-dimensional snapshot from one moment in time. To truly understand how dark energy has shaped the cosmos, we need to watch the movie to see how the universe evolved over billions of years. This is where another brilliant cosmic tool comes into play, one that turns the large-scale structure of the universe into a precise historical record. It's called Baryon acoustic oscillations, or BAO, and it relies on a fossilized echo from the dawn of time that is permanently stamped across the sky. To understand BAO, we need to go back to that same early universe we see in the CMB, when everything was a hot, dense, roiling plasma. In this primordial soup, ordinary matter, the protons and neutrons that scientists call baryons, was tightly coupled with light or photons. Gravity was constantly trying to pull the matter together into clumps, but the intense radiation pressure from the photons was pushing back out, creating a powerful tug of war. This battle set up a series of rhythmic, spherical pressure waves that radiated outward through the plasma, much like sound waves moving through air. These were literal sound waves coursing through the infant cosmos, a deep, resonant hum accompanying the birth of the universe. This cosmic symphony couldn't last forever. When the universe cooled enough to form neutral atoms, a pivotal event known as recombination, the music suddenly stopped. The photons decoupled from the matter and streamed away, becoming the CMB we see today. But at that exact moment, the sound waves were frozen in place, their progress abruptly halted. They left behind a lasting imprint, spherical shells of matter that had been pushed outward by the pressure waves, each shell surrounding an original, slightly denser region. The distance these waves managed to travel before the universe became transparent became a fixed, standard ruler. That distance is about 500 million light-years across. This isn't just a theoretical idea. It's a specific, measurable scale that was permanently etched into the distribution of all the matter in the universe. Fast forward nearly 14 billion years, the universe has expanded by a factor of 1,000, and those spherical shells of matter have expanded with it, stretching to a colossal scale of about 500 million light-years. The galaxies that formed over cosmic time didn't appear randomly. They preferentially formed along these now ancient, fossilized sound waves. This means that if we could map the positions of millions of galaxies in 3 dimensions, we would find a subtle but detectable statistical preference for galaxies to be separated by this specific, scaled-up distance. It's as if the universe has a faint, invisible grid underlying all its structure, and the spacing of the grid lines is this standard ruler from the dawn of time. This is the genius behind the BAO technique. Astronomers don't need to know how bright a galaxy is or what it's made of. They just need to measure its position in space. By conducting massive, painstaking surveys to map the 3-dimensional locations of vast numbers of galaxies, they can search for this preferred scale. Projects like the Sloan Digital Sky Survey have done exactly this, using telescopes to meticulously record the redshifts and positions of millions of galaxies, building a cosmic map of unprecedented scale and detail. When they analyze this map, the signal is unmistakable. There is a clear statistical excess of galaxy pairs separated by the BAO scale, a ghostly echo of those primordial sound waves still visible in the modern universe. This fossilized echo becomes an incredibly powerful tool for measuring dark energy. Here's how it works. We know the true physical size of the standard ruler from our understanding of the early universe, which is beautifully confirmed by the detailed patterns in the CMB. Then, by measuring the apparent angular size of this ruler on the sky at different distances, and thus different epochs in cosmic history, we can determine how much the universe has expanded between that time and now. It's a purely geometric measurement. Imagine you had a ruler of a known length and you held it up at different distances from your eye. The farther away you moved it, the smaller it would appear. By measuring how small it appears, you can calculate exactly how far away it is. BAO allows us to do this on a cosmic scale, using the universe's own imprint as the ruler. This provides a completely independent and incredibly robust check on the expansion history. It doesn't rely on the brightness of objects, so it's immune to the uncertainties that can affect supernova measurements, like intervening dust or potential evolutionary changes in the supernova themselves. The BAO signal is clean, direct, and based solely on geometry. When astronomers measure this signal at various redshifts, they can construct a history of the universe's expansion, and the results powerfully confirm the story told by the supernova. The expansion was indeed slower in the past and has accelerated over the last several billion years, precisely the effect we attribute to dark energy. Furthermore, by comparing the BAO measurements in different directions, scientists can even probe the geometry of dark energy itself. Is it perfectly uniform and smooth, as the cosmological constant model suggests? The BAO data strongly supports this idea, showing that the ruler appears the same size in all directions, indicating that dark energy behaves consistently across the cosmos. This technique, born from the frozen echoes of the Big Bang, turns the entire large-scale structure of the universe into a precision laboratory. It allows us to trace the subtle influence of dark energy across billions of years, providing a third, independent strand of evidence that, when woven together with supernova and the CMB, creates an undeniable and tightly woven web of proof for the accelerating universe. But light doesn't just tell us where things are. It can also reveal the invisible structures that lie between us and the distant cosmos through a phenomenon so subtle it requires statistics to see. This is the realm of weak gravitational lensing, a powerful technique that turns the entire universe into a giant lensing experiment to map the influence of dark energy itself. To understand it, we return to one of Einstein's most profound insights, that matter and energy warp the fabric of space-time, and this warping dictates how everything, including light, moves through it. We're all familiar with the most dramatic version of this, strong gravitational lensing, where the gravity of a massive galaxy cluster is so powerful it bends the light from galaxies behind it into spectacular arcs and rings like a cosmic magnifying glass. Weak lensing is the far more common but infinitely more subtle cousin of this effect. Instead of creating beautiful, obvious arcs, the gravitational tug of all the matter along the line of sight, the dark matter halos, the galaxy clusters, even the diffuse influence of dark energy imperceptibly distorts the shapes of billions of background galaxies. It doesn't tear light into arcs, it just gives every distant galaxy a barely perceptible stretch, a coherent, statistical squish that aligns with the distribution of the invisible mass doing the pulling. The challenge and the genius of this method lies in its incredible subtlety. The distortion on any single galaxy is vanishingly small, utterly swamped by the galaxy's own natural irregular shape. Imagine trying to measure how a gentle breeze bends the light in your backyard by looking at the shadows of leaves. A single leaf tells you nothing. Its shape is too complex. But if you could measure 1,000,000 leaves and find that, on average, they are all very slightly elongated in the same direction, you could deduce the wind's effect. This is exactly what cosmologists do with weak lensing. They don't look at one galaxy, they look at millions. They use immense digital cameras on powerful telescopes to take deep, wide-field images of the sky, capturing the light from countless faint, distant galaxies. Then, sophisticated computer algorithms analyze the shapes of each and every one of these galaxies, measuring their ellipticity and orientation. The natural shapes of galaxies are random, like the random orientation of leaves on a tree. But the gravitational lensing from intervening matter imposes a tiny, coherent pattern on this randomness. By averaging over these immense numbers, a signal emerges from the noise, a faint, web-like pattern of distortion that traces out the cosmic web of dark matter. This pattern is the shear field, a map of how light has been bent and twisted on its long journey across the universe. This cosmic shear map is incredibly powerful because it doesn't just show us where the mass is. It tells us how the growth of that mass has been influenced by the expansion history of the universe, which is governed by dark energy. Here's the crucial connection. The rate at which cosmic structures like dark matter halos and galaxy clusters form and grow is in a constant battle with the expansion of the universe. Gravity wants to pull matter together to build ever larger structures. Dark energy, with its repulsive effect, works against this. It stretches space, making it harder for matter to clump together and effectively suppressing the growth of structure over time. Weak lensing gives us a way to watch this cosmic tug-of-war play out across billions of years. By measuring the lensing signal at different distances, which means looking at light that left its source at different eras in cosmic history, we can reconstruct how the clumpiness of matter has evolved. If dark energy is a cosmological constant and has been acting with a steady push, the growth of structure will have been suppressed in a very specific way. If dark energy is something dynamic like quintessence, changing in strength over time, it would leave a different fingerprint on this growth history. Weak lensing, therefore, provides a direct test of dark energy's nature that is completely independent of the techniques that measure expansion, like supernova and BAO. It's like having two different witnesses to the same crime. Their stories have to agree. Of course, a measurement this delicate is fraught with immense challenges. The distortions are so tiny that any imperfection in the telescope or camera can create distortions that mimic the lensing signal. This is called systematic error, and it is the nemesis of every weak lensing scientist. The subtle stretching of a galaxy's shape by gravity can be easily mimicked or overwhelmed by distortions from Earth's atmosphere, by slight warping in the telescope's optics, or even by the way the sensitive digital sensors in the camera respond to light. To overcome this, projects must engage in a heroic effort of calibration. They take images of star fields to meticulously map the optical distortions of their telescope. They use advanced physics-based models to understand how the sensors convert light into digital signals and correct for any artifacts. They even run vast simulations of the universe to understand what the pure, uncontaminated lensing signal should look like, so they can better recognize and subtract the noise. This painstaking work is essential to ensure that the faint whisper of a signal they detect is truly from the cosmos and not from their own equipment. The scale of data required is almost incomprehensible. To get a signal strong enough to beat down the statistical noise and control the systematics, you need to measure the shapes of not thousands, not millions, but hundreds of millions of galaxies across huge swaths of the sky. This is why weak lensing is only now coming into its own as a precision cosmological tool. It required the development of technology that didn't exist just a couple of decades ago. Giant digital cameras with billions of pixels, supercomputers to process the data, and complex algorithms powered by machine learning to accurately measure galaxy shapes. Projects like the Dark Energy Survey pioneered these techniques, but they are merely the opening act. The main event is the Vera-C, Rubin Observatory's Legacy Survey of Space and Time, or LSST. Scheduled to begin operations soon, the LSST will feature the largest digital camera ever built for astronomy, with a staggering 3.2 billion pixels. Over 10 years, it will conduct an unprecedented survey of the southern sky, imaging an area equivalent to 40 full moons in a single exposure, and doing so over and over again. It will catalog over 20 billion galaxies and measure the shapes for a significant portion of them, creating the most detailed weak lensing map of the universe ever conceived. This map will allow us to trace the cosmic web with exquisite detail and measure the growth of structure throughout cosmic history with a precision that could finally distinguish between a simple cosmological constant and more exotic models of dark energy. It is a testament to human ingenuity, a project that harnesses imperceptible distortions in the light of ancient galaxies to illuminate the darkest secret of the cosmos. So with all these observational tools at our disposal, supernova, baryon acoustic oscillations, weak lensing, and the cosmic microwave background, we are collecting mountains of data on how the universe expands and how its structures grow. But to make sense of it all, to turn this flood of information into a real understanding of dark energy, we need a way to quantify it. We need a single number that can capture its essential nature, a parameter that tells us how it behaves. This brings us to one of the most important concepts in modern cosmology, the equation of state represented by the letter W. Think of W not as a mysterious symbol, but as the personality profile for dark energy. It's a simple number that describes the relationship between the pressure and the energy density of this mysterious component. In the language of physics, the equation of state is written as pressure equals W times density. For most stuff we're familiar with, this number is straightforward. For regular matter that's just sitting there like dust or a collection of galaxies, the pressure is essentially zero, so W equals zero. For radiation like light, W equals 1/3. But for dark energy, the rules are completely different, and the value of W holds the key to unlocking its identity. The simplest candidate, Einstein's cosmological constant, has a very specific personality. Its W is exactly -1. This value is special because it comes directly from the mathematics of general relativity for a constant vacuum energy. If W equals -1, it means that the pressure is not just negative, it is exactly equal to the negative of the energy density. This has a profound consequence. As the universe expands and new space is created, the energy density of a cosmological constant remains perfectly constant. It never dilutes. This is why it eventually dominates the cosmos. While matter and radiation get thinner and weaker as the universe grows, the energy density of lambda stays the same, its repulsive push becoming ever more powerful over time. A value of W equals -1 paints a picture of a steady, relentless, and unchanging force. But what if dark energy is not so constant? This is where the equation of state becomes a powerful tool for discovery. If W is different from -1, it shatters the simple lambda model and opens the door to dynamic possibilities like quintessence. If W is greater than -1, say -0.9, it suggests a form of dark energy that weakens over time. Its energy density would decrease as the universe expands, though not as quickly as matter. This could point to a quintessence field that is slowly fading. potentially allowing the expansion to eventually slow down more than in the lambda scenario. On the other hand, if W is less than -1, this is where things get truly wild. This is the realm of so-called phantom dark energy. In this model, the energy density of dark energy would actually increase as the universe expands. This would lead to an even more violent and catastrophic end than the Big Freeze, a big rip where the accelerating expansion becomes so intense that it tears apart every structure from galaxies to atoms in a finite time. The simple parameter W, a single number, can therefore tell us the ultimate fate of everything. The monumental effort in cosmology right now is to measure this number with ever-increasing precision. We are not just trying to see if W is -1. We are trying to measure it to the second, third, or even fourth decimal place. Current constraints from combining all the data from supernova, BRO, weak lensing, and the CMB tell us that W is incredibly close to -1. The latest results from the Dark Energy Survey and the Planck satellite suggest a value around -1.03, plus or minus a few hundredths. This is a stunning confirmation of the simplest model, but that error bar, that tiny range of uncertainty, is where all the excitement lies. The data is consistent with a cosmological constant, but it hasn't yet ruled out the possibility that W is, for example, -0.98 or -1.02. That sliver of possibility is what keeps physicists searching. It's the difference between a universe governed by a static, eternal constant and one driven by an evolving, dynamic field. The next generation of telescopes, like Euclid and the Roman Space Telescope, are designed specifically to shrink that error bar down to a precision of about 1% or even better. If W is exactly -1, that will be a monumental discovery, solidifying the cosmological constant as a fundamental feature of reality. But if those ultra-precise measurements find a definitive deviation, even a tiny one, it would be a revolution, forcing us to completely rewrite our understanding of physics and embrace a new, dynamic cosmos. This single parameter transforms the philosophical mystery of dark energy into a hard, empirical, and testable scientific question. Now that we have a way to quantify dark energy's behavior, it's crucial to place it in the broader cosmic context. We've been focusing on this mysterious accelerating force, but it doesn't exist in a vacuum. It shares the cosmic stage with another, equally enigmatic player, dark matter. Their names are so similar it's easy to confuse them, but in reality, they are cosmic partners in mystery, two invisible entities with completely opposite personalities and roles, locked in a tug-of-war that has shaped the entire history of the universe. Think of the cosmos as a grand theatrical production. In this play, dark matter is the stage crew and the scaffolding. It's the unseen force that builds the structures. Dark energy, on the other hand, is like a powerful, unseen wind that's slowly and relentlessly pushing the entire stage apart, forcing the actors farther away from each other. One is all about pulling things together, the other is all about pushing them apart. This fundamental difference starts with how they interact with the universe. Dark matter does interact through gravity, and it does so very strongly. It's a clumpy, gathering force. Its gravitational pull is what initially gathered the primordial hydrogen gas after the Big Bang, forming the first protogalactic cloud. Without dark matter's gravitational glue, the mutual gravity of the ordinary matter, the stuff that makes up stars, planets, and us, would have been far too weak to overcome the expansion of the universe and collapse into galaxies. Dark matter provided the gravitational backbone for the entire cosmic web, the invisible skeleton upon which the visible universe is draped. Dark energy couldn't be more different. It doesn't clump, it doesn't gather, It is perfectly smooth and uniform, a featureless energy infused into the very fabric of space itself. And while dark matter uses gravity to pull, dark energy creates a repulsive effect that pushes. For most of cosmic history, dark matter was the dominant force on large scales. Its gravity was slowing down the expansion, doing its best to pull everything back together. But as the universe expanded, the density of matter, both dark and normal, diluted. The density of a cosmological constant dark energy, however, stayed the same. Imagine two runners. One is matter, who gets tired and slows down over time. The other is dark energy, who maintains a constant, relentless pace. About 5 billion years ago, the universe had expanded enough that the density of matter dropped below the constant density of dark energy. In that moment, dark energy took the lead in the cosmic race. Its repulsive push overcame gravity's pull, and the expansion of the universe began to accelerate, a state it has been in ever since. This leads us to the cosmic budget, the inventory of everything in the universe. When cosmologists add it all up, the result is both humbling and astonishing. All the stuff we know and love, every star in every galaxy, every planet, every black hole, every human being, and every atom in our bodies, makes up a mere 4.9% of the total content of the cosmos. We are not even a rounding error. We are the cosmic frosting on an invisible cake. Dark matter makes up about 26.8%. It is 5 times more abundant than all the ordinary matter, which is why its gravitational influence is so paramount in holding galaxies and clusters together. And then there's dark energy, the undisputed heavyweight champion of the universe, accounting for a staggering 68.3% of everything. This means that nearly 70% of the universe is composed of a force that we cannot see, touch, or directly interact with, whose sole effect seems to be driving the cosmos apart. So why do they share the dark in their name? It's a label of ignorance, a confession that we don't fully understand either of them, but the reason for their darkness is slightly different for each. Dark matter is dark primarily because it does not interact with electromagnetic force. It doesn't absorb, reflect, or emit light. It is completely transparent and invisible to our telescopes. We know it's there only because of its gravitational effects. It bends light through gravitational lensing, and its gravitational pull dictates how galaxies and galaxy clusters move. Dark energy is dark for an even more profound reason. It doesn't seem to interact with anything in any way we can detect, except on the grandest scale of all, the geometry of spacetime itself. It doesn't clump, it doesn't form particles, it doesn't scatter light. We only infer its existence from its effect on the expansion rate of the entire universe. Both are invisible, but one reveals itself through its gravitational pull on structures, while the other reveals itself through its push on the cosmos as a whole. Understanding this interplay is absolutely key to decoding our past and our future. In the early universe, dark matter's gravity was the great architect, drawing matter together to form the first galaxies and the vast web-like structures we see today. Dark energy was present, but its effect was negligible, like a whisper in a storm. As the universe aged and expanded, the storm of matter diluted, and the whisper of dark energy grew into a prevailing wind. Today, that wind is shaping the future. It is suppressing the formation of new giant structures by making it harder for gravity to pull matter together across vast cosmic distances. And it will ultimately determine the final fate of everything. The balance between these two dark components, the puller and the pusher, is what writes the story of the cosmos, a story we are only just beginning to read by meticulously measuring their effects on the light from distant stars and the echoes of the Big Bang. So the fate of the entire cosmos, the ultimate destiny of every star, every planet, and every atom, hinges entirely on the precise nature of this mysterious dark energy. It all boils down to that one crucial number we discussed, the equation of state parameter W. This single value acts as a cosmic dial, and where it's set determines which of three profoundly different futures awaits our universe. The first and currently most favored scenario is what cosmologists call the Big Freeze, also known as heat death. This future unfolds if dark energy is indeed a true cosmological constant, with W exactly equal to -1. In this case, the accelerated expansion continues at a steady, relentless pace forever. Billions of years from now, the universe will be a much darker, colder, and lonelier place. As galaxies rush away from each other at ever-increasing speeds, the observable universe, the sphere of space from which light can still reach us, will actually shrink. Distant galaxies will first have their light redshifted into invisibility, and then they will be pushed beyond our cosmic horizon entirely. The night sky, which today is filled with the faint glow of countless stars and galaxies, will eventually go completely black. Our own Milky Way will have long since merged with the Andromeda Galaxy to form a giant elliptical galaxy, which we might call Milkomda. But even this new home will not last forever. Over trillions of years, the stars within it will slowly burn out. The massive ones will explode as supernova. The smaller ones, like our Sun, will fade into white dwarfs and then eventually cool into cold black dwarfs. The interstellar gas needed to form new stars will have been used up or expelled, and star formation will cease entirely. Eventually, even the black holes, the last bastions of structure, will slowly evaporate away through Hawking radiation. The universe will approach a state of absolute thermodynamic equilibrium, a uniform, frigid sea of diluted particles and radiation, just a fraction of a degree above absolute zero. There will be no more energy gradients, no more work to be done, no more change. It is a quiet, gradual, and eternal fading into nothingness. The second possibility is far more violent and dramatic, the Big Rip. This apocalyptic scenario becomes possible if dark energy is not a constant, but is instead a form of phantom dark energy where the equation of state is less than -1, meaning W is less than -1. In this model, the energy density of dark energy doesn't just remain constant, it actually increases as the universe expands. This leads to an acceleration that isn't just steady, it's exponentially self-reinforcing. The repulsive force becomes so powerful that it doesn't just push galaxies apart, it overcomes all the forces that hold structures together. The end would not be a slow fade, but a catastrophic shredding of the cosmos itself. First, the accelerating expansion would tear apart the cosmic web. Galaxy clusters, bound by the relatively weak force of their mutual gravity, would be the first to be pulled apart. Then, individual galaxies like our own Milky Way would be ripped to pieces. As the force continues to intensify, it would overcome the much stronger gravitational pull holding solar systems together. The Sun would be torn from its orbit around the galactic center, and Earth would be ripped from its orbit around the Sun. In the final moments, the terrible force would exceed the electromagnetic forces that hold atoms together. Planets and stars would be vaporized. Finally, in the last fraction of a second, molecules, atoms, and even atomic nuclei would be torn apart. The universe would end not with a whimper, but with a literal rip in the fabric of spacetime itself, a silent flash where everything is dissolved into its most fundamental components. It's a terrifyingly abrupt end, and its possibility reminds us that the cosmos can be as violent as it is beautiful. The third scenario is the most remote, but it's the one that appeals to a sense of cosmic cycle, a big crunch. This would require dark energy to be a dynamic field like quintessence that weakens over time. If W were to become greater than -1 and its energy density were to diminish, the repulsive push could fade away. Gravity, the great attractor, would once again take the reins. The expansion of the universe would gradually slow down, stop, and then reverse. Every galaxy would begin rushing toward every other galaxy. The redshift we see today would be replaced by a blueshift as the universe collapses in on itself. This contraction would be the mirror image of the Big Bang, often called the Big Crunch. As everything piles together, the temperature and density of the universe would soar to incredible levels. The cosmos would become a cosmic pressure cooker, potentially melting all structure back down into a hot, dense state similar to how it began. Some theories even suggest this could be part of an eternal cycle, a big bounce where the universe collapses down to a point and then rebounds in a new Big Bang, giving birth to a new universe from the ashes of the old. It's a poetic idea, a universe with seasons of expansion and contraction, death and rebirth. However, all current observational evidence makes this the least likely of the three fates. The data strongly points to an acceleration that is not slowing down, making a turnaround toward a crunch seem improbable. The incredible thing is that these aren't just philosophical thought experiments. They are scientific predictions that stem from the hard data we are collecting right now. The evidence from the cosmic microwave background to the large-scale structure maps currently favors the first scenario, the big freeze driven by a cosmological constant. The measured value of W is incredibly close to -1, but that word close is where all the suspense lies. Our measurements still have a margin of error. That uncertainty, that tiny window of possibility, is what fuels multi-billion-dollar missions like the Euclid Telescope and the Vera C. Rubin Observatory. They are designed to measure W with such exquisite precision that they can finally tell us if it is exactly -1, or if it deviates just enough to point us toward a rip or hint at a fading quintessence. We are, in a very real sense, measuring the fate of everything. This connects the most abstract equations of theoretical physics to the most profound existential questions a person can ask. What is our ultimate purpose in a universe that might end in ice, fire, or cycles? The quest to decode dark energy is more than a scientific pursuit. It is a fundamental human drive to understand our story from beginning to end, to find our place in a narrative whose final chapter is yet to be written. But this grand cosmic story, with its three possible endings, leads us to one of the most perplexing and deeply philosophical questions in all of science: why now? We live at an incredibly special moment in the 13.8 billion-year history of the universe, a brief sliver of time where the conditions are just right for us to not only exist, but to look up and contemplate the cosmos itself. This is known as the cosmic coincidence problem, and it revolves around the astonishingly perfect timing of dark energy's rise to power. For the first 9 billion years after the Big Bang, the universe was dominated by matter. Its gravitational pull was controlling the expansion, slowing it down, allowing galaxies to form, stars to ignite, and planets to coalesce. It was during this long, fertile era that the complex chemistry of life had the time and stability to arise. Then, about 5 billion years ago, the balance of power shifted. The density of matter, which dilutes as the universe expands, finally dropped below the constant density of dark energy. This is the moment the acceleration began. Here's the stunning coincidence. We emerged as conscious observers right around the same time that this cosmic transition occurred. The era where dark energy becomes dominant and the era where intelligent life can evolve overlap almost perfectly. This seems too convenient to be random. If dark energy had asserted its dominance much earlier, say just a billion years after the Big Bang, its repulsive push would have been catastrophic. It would have ripped apart the delicate protogalactic clouds before they could ever collapse into galaxies. Stars and planets would never have formed, and the universe would be a dark, empty, and ever-accelerating void, devoid of any structure or life. On the other hand, if dark energy's influence had been much weaker and only became dominant tens of billions of years in the future, the universe might have faced a different fate. A slower expansion might have allowed gravity more time to pull everything back together, potentially leading to a big crunch long before complex life could evolve. Or life might eventually arise in a much older, more evolved cosmos, but we clearly aren't there. We are here now, at this precise moment when the universe is still full of light from galaxies, but the acceleration has just begun, making it detectable to our telescopes. This fine-tuning is breathtaking. The measured value of dark energy's density is incredibly small, but if it were even slightly larger or smaller by a factor of just a few, the universe would be utterly unrecognizable and almost certainly lifeless. So why does the universe appear to be so exquisitely tuned for our existence? One provocative line of reasoning is the anthropic principle. In its simplest form, it states that the universe must be compatible with the conscious life that observes it. We should not be surprised to find that the fundamental constants of nature, like the strength of dark energy, are set to values that allow for our existence, because if they weren't, we wouldn't be here to wonder about it. It sounds almost like a tautology, but it gains profound weight when combined with the theory of the multiverse. If our universe is just one bubble in a vast, perhaps infinite, multiverse, a cosmic landscape where each universe is born with different physical laws and constants, then the coincidence problem simply evaporates. In most of these universes, the dark energy density is probably too high or too low, and those universes remain dark, empty, or short-lived, with no one to witness them. But by pure statistical chance, a few universes will have the right, rare combination of parameters to allow galaxies, stars, planets, and life to form. We inevitably find ourselves in one of those habitable universes, not because it was designed for us, but because we are a product of its specific, life-friendly conditions. Our universe isn't uniquely fine-tuned. It's just one that won the cosmic lottery. This is a powerful, if speculative, explanation. Yet, it makes many scientists deeply uncomfortable because it can feel like a retreat from the traditional goal of physics, to find a unique, predictive theory that explains why the constants must have the values they do. The multiverse idea is currently untestable, as we have no way of observing these other universes. It risks explaining one mystery by invoking an even bigger one. The coincidence problem, therefore, is more than just a puzzle about dark energy. It is a gateway to the deepest questions about reality. It forces us to confront whether the laws of nature are inevitable and unique, or if they are merely a local bylaw in a much grander, more random cosmic arena. It suggests that the answer to why the universe is the way it is might be inextricably linked to the fact that we are here to see it. Yet even as we grapple with these grand cosmic fates, a far more immediate and profound mystery confronts physicists in the here and now, a problem so severe it has been called the worst theoretical prediction in the entire history of science. This is the cosmological constant problem, and it strikes at the very heart of our understanding of reality, forcing us to confront the unsettling possibility that what we call empty space is anything but empty. According to our most fundamental theories of how the universe works at the smallest scales, the vacuum of space should be a seething, bubbling cauldron of energy. Quantum field theory tells us that so-called empty space is not a true void. It is alive with a constant frenzy of activity. At every single point, pairs of virtual particles are constantly flickering into and out of existence, borrowing energy from the vacuum for unimaginably brief moments before annihilating each other and returning it. This isn't some abstract concept. We see the effects of this quantum foam in laboratory experiments every day. It's responsible for measurable effects like the Casimir force, where two metal plates placed incredibly close together in a vacuum are gently pushed toward each other because the quantum fluctuations between the plates are restricted compared to the riot of activity outside them. All of this frantic, temporary creation and destruction should add up. It should contribute a vast, enormous energy to the very fabric of space itself, a background energy density that permeates the entire cosmos. This is the vacuum energy predicted by quantum mechanics, and when physicists sit down with their pencils and paper to calculate what this energy density should be, based on our well-tested theories of the quantum world, they arrive at a number. Then they turn to their telescopes and use the expansion rate of the universe, the cosmic microwave background, and the large-scale structure of galaxies to measure the actual energy density of dark energy that we observe. The two numbers should be the same, but they are not. They are not even close. The value calculated from quantum field theory is a staggering 10 to the power of 120 times larger than the value we actually measure. That's a 1 with 120 zeros after it. To put that incomprehensible discrepancy into perspective, it's the difference between predicting that the entire observable universe should be made of pure energy and observing that the actual value is less than the energy contained in a single grain of sand. It is an error so colossal, so breathtakingly vast, that it would be funny if it weren't so deeply troubling. It means that our two most powerful and successful theories, quantum mechanics, which describes the very small, and general relativity, which describes the very large, are fundamentally, catastrophically at odds when they meet in the vacuum of space. This isn't a small puzzle to be solved with a tweak to an equation. It is a 5-alarm fire in the foundations of physics. It suggests one of two terrifying possibilities. Either our method for calculating the energy of the quantum vacuum is profoundly and completely wrong in a way we don't yet understand, or something truly bizarre is happening. The second possibility is that the calculation is theoretically correct, and the quantum vacuum does possess this unimaginably huge energy, but some mysterious, precise, and perfectly balanced cancellation mechanism is at work, neutralizing almost all of that incredible energy to leave behind the tiny, faint whisper that we detect as dark energy. This would be a cancellation of 1 part in 10 to the 120, a level of fine-tuning so exquisite, so utterly perfect, that it seems absurd to attribute it to chance. It would be like balancing a pencil on its tip on the surface of the moon and having it remain perfectly upright for billions of years. This is the core of the cosmological constant problem. Why is the observed effect of vacuum energy so inconceivably small compared to its theoretical prediction? This glaring failure of our theories has sent physicists scrambling for solutions, and the proposals are as ambitious as the problem is large. One promising avenue is supersymmetry, an elegant theoretical framework that posits every known particle has a hidden superpartner particle. In a perfectly supersymmetric universe, the contributions of particles and their superpartners to the vacuum energy would perfectly cancel each other out, resulting in a net energy of 0. This would solve the problem neatly. However, we don't live in a perfectly supersymmetric universe. If these superpartners exist, the symmetry must be broken at the energy levels we can observe, meaning the cancellation wouldn't be perfect. But it could bring the prediction much, much closer to the observed value, which would be a monumental step forward. The frustrating catch is that despite decades of searching, no evidence for these superpartner particles has been found in our most powerful particle colliders. Other theorists suggest the answer might lie in the very nature of gravity itself. Perhaps Einstein's general relativity, for all its success, is not the final word on how gravity works. Maybe it needs to be modified when applied to the quantum vacuum, or perhaps gravity somehow doesn't couple to vacuum energy in the way we currently assume. This idea pushes us toward the long-sought-after theory of quantum gravity, a single framework that seamlessly unites the quantum world with the gravitational one. String theory and loop quantum gravity are two leading candidates for such a theory, and both attempt to address the vacuum energy problem by fundamentally rethinking the nature of spacetime at the Planck scale, the smallest possible size. In these approaches, the smooth continuum of space and time described by Einstein gives way to a discrete, granular structure, a spacetime foam, which could potentially place a natural cutoff on the energy of quantum fluctuations, preventing it from reaching those insane levels. The challenge, of course, is that these theories operate at energy scales so far beyond our current ability to test that they remain in the realm of beautiful, speculative mathematics. The cosmological constant problem is more than just an academic curiosity. It is a stark reminder of the limits of our knowledge. Dark energy is not just a mysterious component of the universe. It is a glaring signpost pointing toward a deeper layer of reality that we have not yet uncovered. It forces us to admit that we truly do not understand the nature of nothingness. The void is not empty. It is filled with an energy that holds the key to the fate of the cosmos, and its value is the most precisely tuned number we have ever encountered in nature. Solving this problem will require nothing less than a revolution in physics, a new paradigm that will likely reshape our understanding of everything from the fabric of spacetime to the origin of the universe itself. It is a humbling challenge, but also an exhilarating one, reminding us that the greatest mysteries often lie hidden in plain sight, even in the apparent emptiness between the stars. But what if the entire premise is wrong? What if we're not missing some mysterious energy, but are instead misunderstanding the fundamental force that governs the cosmos? This is the radical proposition at the heart of modified gravity theories, a complete paradigm shift that suggests dark energy isn't a real substance at all, but a phantom, an illusion created by our own incomplete understanding of how gravity works on the largest imaginable scales. For over a century, Einstein's theory of general relativity has been the undisputed king of cosmology, passing every test with flying colors, from the bending of starlight around the sun to the precise orbits of binary pulsars. Its predictions have been verified again and again. But what if this magnificent theory, like Newton's laws before it, is only an approximation? What if it breaks down when applied to the entire universe? This isn't a fringe idea. It's a serious, though contentious, line of inquiry pursued by physicists who are willing to ask the heretical question: could we be misreading the universe's acceleration? The most straightforward modified gravity approach is often called F of R gravity. The name comes from the mathematics. It proposes that the gravitational force isn't just determined by the curvature of spacetime represented by R in Einstein's equations, but by a more complex function of that curvature, Fr. In simple terms, it suggests that gravity behaves differently in regions of extremely low density like the vast, near-empty voids between galaxy clusters than it does in the high-density environments of stars and planets where we've tested it. In these cosmic deserts, the theory proposes, gravity could naturally become slightly repulsive. This tiny change, when added up across billions of light-years, could mimic the effect of a dark energy push, causing the universe's expansion to accelerate without needing to invoke any new, invisible component. It's not that space is being pushed apart by a mysterious energy. It's that the attraction between masses weakens in a specific way over these enormous distances, making it appear as if something is pushing them apart. Another fascinating inspiration comes from a theory designed to solve a different cosmic mystery right here in our own galactic backyard. It's called MUND, which stands for Modified Newtonian Dynamics. Proposed in the 1980s to explain why the outer stars of galaxies rotate faster than expected without requiring dark matter, MUND suggests that Newton's law of gravity changes at extremely low accelerations. While MUND itself was designed for galaxies and can't explain cosmic expansion, its success on that scale has inspired cosmologists to wonder if a similar principle, a modification of Einstein's relativity rather than Newton's gravity, could work on the scale of the entire universe. These relativistic extensions of MUND aim to create a single, unified framework that explains both the rotation of individual galaxies and the acceleration of the cosmos, all without the need for either dark matter or dark energy. It's a breathtakingly ambitious goal, a theory of gravity that works from the solar system to the edge of the observable universe, rendering two of cosmology's greatest mysteries obsolete in one fell swoop. The appeal of these theories is immense. They offer a stunningly elegant solution to the fine-tuning problems that plague the dark energy model. There is no longer a need to explain why the vacuum energy is 120 orders of magnitude smaller than its predicted value, because there is no vacuum energy. The cosmological constant problem simply vanishes. The "why now" coincidence also loses its sting. In these models, the apparent acceleration isn't triggered by the density of matter dropping below a certain threshold. It's an inherent feature of how gravity operates across cosmic distances, and its effects become noticeable only as the universe grows large and diffuse enough for those modified gravitational forces to dominate. This approach appeals to a sense of parsimony, the idea that the simplest explanation is often the best. Instead of inventing two completely new, invisible substances, dark matter and dark energy, that make up 95% of the universe, maybe we just need to adjust our theory of the one force we thought we knew. However, this radical elegance comes with equally massive challenges. The primary hurdle is that any new theory of gravity must not only explain the new, puzzling phenomena, but also perfectly reproduce all the stunning successes of Einstein's general relativity that we already observe. It's like asking a new champion to not only win a new race, but to also match every record the old champion ever set. For instance, general relativity perfectly predicts the precise orbital decay of the Hulse-Taylor binary pulsar due to gravitational waves. Any modified gravity theory must get that exactly right. It must also account for the famous bending of light around massive objects, the precise timing of signals from GPS satellites, and the dynamics of our own solar system. Building a theory that alters gravity on cosmic scales while leaving it untouched on smaller scales is an incredibly difficult balancing act. Many proposed modifications fail this test, producing effects that would have been detected in our own celestial neighborhood if they were true. The most stringent tests come from the wealth of cosmological data we now possess. A successful modified gravity theory must do more than just explain the accelerating expansion seen in supernova. It must also simultaneously reproduce the detailed patterns of the cosmic microwave background, the specific clustering of galaxies revealed by baryon acoustic oscillations, and the way cosmic structures grow over time as measured by weak gravitational lensing. This is a multi-front war, and no modified gravity theory has yet won a decisive victory on all fronts. Some can tweak their parameters to fit one set of data, like the supernova distances, but then they fail to match the precise peak structure of the CMB or the observed amount of gravitational lensing. The standard lambda CDM model, with its dark matter and dark energy, isn't just a story. It's a detailed, quantitative recipe that matches a breathtaking array of independent observations. To overthrow it, a challenger must be even better. This doesn't mean the quest is hopeless. The fact that our current model requires 95% of the universe to be made of undetectable substances is a powerful motivation to keep exploring these alternatives. The ongoing tension in measuring the current expansion rate of the universe, known as the Hubble Tension, could be another hint that something is amiss in our standard model, perhaps pointing toward new physics that a modified theory of gravity could provide. The search for these theories is a vital part of science. It's the process of stress testing our most fundamental assumptions. Even if they ultimately fail to replace the dark energy paradigm, the effort to build them deepens our understanding of gravity itself and forces us to ask better questions. They represent the boldest kind of scientific creativity, a willingness to tear down the entire framework and start from scratch rather than just adding new pieces to the puzzle. It is a high-stakes gamble that reminds us that in our quest to decode the cosmos, we must be prepared for the possibility that our most cherished ideas, even those as brilliant as Einstein's, might only be part of a much larger, more revolutionary truth. But if modifying gravity is one radical path, then string theory offers another, one that is even more mind-bending and vast in its implications. This approach doesn't try to eliminate dark energy. Instead, it tries to explain its oddly tiny value by proposing that our entire universe is just one small part of a much grander, multidimensional reality. String theory is a candidate for the long-sought theory of everything, an attempt to reconcile general relativity with quantum mechanics. Its core idea is that the fundamental building blocks of nature are not point-like particles but incredibly tiny, vibrating strings. The different ways these strings vibrate give rise to all the different particles and forces we observe, from electrons to photons. But for this mathematical elegance to work, the theory requires something extraordinary. The universe must have more than the three spatial dimensions we experience. It needs extra dimensions, 6 or 7 of them, curled up into a space so small we could never hope to see them directly. This concept of hidden dimensions might sound like pure science fiction, but it leads to a profound possibility for explaining dark energy, the landscape of vacua. In string theory, the way these extra dimensions are folded and curled, their shape and size determines the fundamental constants of nature within any given universe, including the value of the cosmological constant. The twist is that there isn't just one way for these dimensions to curl up. The number of possible stable configurations is astronomically vast, perhaps around 10 to the 500th power. This is not just a big number. It is a number so large that it dwarfs the number of atoms in the observable universe. Each of these configurations corresponds to a different universe with its own unique physical laws and constants. In the overwhelming majority of these universes, the vacuum energy is enormous and positive, leading to a universe that tears itself apart in a fraction of a second, or enormously negative, causing an immediate gravitational collapse. But in an incomprehensibly tiny fraction of these possibilities, the numbers come out just right for a universe that is long-lived and capable of supporting life. We, of course, find ourselves in one of those rare, habitable universes where the dark energy value is small and non-lethal. In this string theory landscape, the incredible fine-tuning of dark energy is no longer a mystery, it is a selection effect. We observe this specific value not because it is fundamental or required by theory, but because it is the only type of value that allows for galaxies, stars, planets, and ultimately, observers like us to exist. Another dazzling idea emerging from string theory is the concept of brane worlds. The name comes from the word membrane. In this scenario, our entire three-dimensional universe could be a three-dimensional membrane floating within a higher dimensional space called the bulk. All the particles and forces we know, with the possible exception of gravity, might be trapped on this brane, which is why we are so exquisitely aware of 3 dimensions of space and 1 of time. Gravity, however, could be a force that permeates all dimensions, leaking off our brane and into the bulk. This leakage could explain why gravity is so weak compared to the other fundamental forces. But what does this have to do with dark energy, the energy inherent in the brane itself, or the forces acting between our brane and other branes floating in the bulk, could manifest itself in our 4-dimensional world as a form of dark energy? The acceleration of the universe might not be driven by an energy within space, but by the dynamics of our entire universe as a membrane interacting with this larger hidden reality. The push could be coming from outside, a cosmic tension between membranes in a higher dimensional arena. These ideas are, without a doubt, among the most speculative in all of modern physics. They are currently untestable through direct experiment, residing in the realm of elegant mathematics and profound theoretical possibility. They do not so much solve the cosmological constant problem as they reframe it, trading a problem of physics for a problem of statistics and existence within a multiverse. Yet their value is immense. They serve as a powerful reminder that our perspective on the cosmos might be incredibly provincial. The force we call dark energy, which seems so dominant and mysterious from our limited 4-dimensional viewpoint, might be a mere side effect, a shadow cast by the true workings of a higher dimensional reality. It challenges us to think not in terms of finding a missing component within our universe, but in terms of our universe being the component within a far vaster and more exotic structure. The quest to decode dark energy, therefore, might be our first real glimpse into the architecture of the multiverse, a hint that the deepest layers of reality are stranger and more wonderful than we ever imagined. So the theoretical battleground is set, with brilliant minds proposing everything from new energy fields to radical revisions of gravity itself. But cosmology is a science driven by data, not just elegant equations. To move from speculation to discovery, we need to observe the universe with a clarity and precision that was once unimaginable. This isn't a task for a single telescope or a lone team of scientists. It requires a global generation of entirely new eyes on the sky, a coordinated armada of missions designed to hunt dark energy from every possible angle. We are now on the cusp of this new golden age of observation, with a fleet of next-generation observatories poised to launch or already scanning the heavens, each armed with a specific plan of attack to corner this cosmic mystery. Leading the charge from the darkness of space is the European Space Agency's Euclid telescope, a mission named for the ancient Greek father of geometry, a fitting tribute for a craft designed to measure the shape of the universe itself. Launched in July of 2023, Euclid is a unique and powerful hybrid. It doesn't have the single, massive mirror of the James Webb Space Telescope. Instead, its power lies in its ability to see an enormous swath of the sky at once with incredible sharpness, free from the blurring effects of Earth's atmosphere. Over its planned 6-year mission, Euclid will perform a cosmic census on a staggering scale, measuring the precise positions and shapes of over 1 billion galaxies across more than a third of the sky. Its primary weapons are weak gravitational lensing and baryon acoustic oscillations. By mapping the subtle distortions in the shapes of these distant galaxies, it will create the most detailed map ever made of the dark matter distribution, which is sculpted by the influence of dark energy. Simultaneously, by detecting the faint, fossilized imprint of those ancient sound waves in the clustering of galaxies, it will chart the expansion history of the universe with unparalleled geometric precision. Euclid's genius is in its dual approach, using two completely independent methods to measure the same thing, allowing for powerful cross-checks that will ruthlessly eliminate systematic errors and deliver a result of breathtaking reliability. Meanwhile, back on the ground, an equally colossal project is preparing to open its eye to the cosmos. Perched atop a mountain in Chile, the Vera C. Rubin Observatory is a monument to scale and speed. Its centerpiece is the Legacy Survey of Space and Time, or LSST, and it will be conducted by the largest digital camera ever built for astronomy, a behemoth weighing nearly 3,000 kilograms with a resolution of 3.2 billion pixels. To put that in perspective, it would take over 800 standard high-definition television screens to display just one of its full-size images. But the LSST power isn't just in its resolution, it's in its relentless pace. Over 10 years, this camera will photograph the entire available southern sky every few nights, creating an unprecedented time-lapse movie of the universe. It will not just map billions of galaxies for weak lensing and BO studies. It will discover and track millions of transient objects, most notably Type Ia supernova. By finding these standard candles in unprecedented numbers and tracking their brightness over time, the LSST will construct a supernova-based expansion history that is vastly more detailed and far-reaching than the original discoveries from the 1990s. This survey will be so comprehensive that it will effectively watch the universe evolve in real time, offering a dynamic view of dark energy's influence that static snapshots simply cannot provide. Scheduled to join this effort in space around 2027 is NASA's Nancy Grace Roman Space Telescope, named for the agency's first chief astronomer, who is often called the mother of the Hubble telescope. Roman is designed to be a wide-eyed hunter, combining the infrared sensitivity of the James Webb Space Telescope with a field of view 100 times larger than Hubble's. This makes it uniquely suited for two key tasks. First, it will conduct a massive high-resolution survey for weak gravitational lensing, providing a space-based complement to the Rubin Observatory's ground-based work, but without atmospheric distortion, allowing for exquisitely precise shape measurements of distant galaxies. Second, and perhaps most crucially, it will embark on a monumental search for distant Type Ia supernova. Roman's infrared vision is key here, as it can see through the cosmic dust that can dim and redden the light of these explosions, a major source of uncertainty in past measurements. By discovering thousands of these supernovae deep into the infrared, Roman will measure the expansion history with a precision that could finally detect the slightest deviation from the cosmological constant model, potentially revealing the dynamic nature of quintessence. The true brilliance of this new era lies not in competition but in powerful, deliberate synergy. These are not rival projects, they are a pre-planned alliance. Euclid, with its razor-sharp, wide-field view from space, is mapping the geometry of the dark universe. The Rubin Observatory, from its mountain perch, is capturing the dynamic sky, watching for the telltale flashes of supernova and measuring the lensing signal across a vast volume. The Roman Space Telescope will then follow up, using its infrared eyes to peer deeper and cleaner, verifying and refining the measurements of its partners. Together, they form a trifecta of discovery. They will measure the expansion history of the universe using supernova, they will measure the growth of structure through weak lensing, and they will measure the geometry of the cosmos through baryon acoustic oscillations. By combining these three independent lines of evidence, scientists will be able to perform our ultimate test on the equation of state of dark energy, constraining its value W with a precision of 1% or even better. This is the level of accuracy needed to finally distinguish between a simple, unchanging cosmological constant and a dynamic field that evolves over time. Within the next decade, the data flowing from this coordinated campaign will provide the evidence that could confirm our current model of the cosmos, or, far more excitingly, force us to tear up the textbooks and start a whole new chapter in our understanding of the universe. The tools are being deployed. The hunt for the universe's greatest secret is entering its final, decisive phase. But how do we test these grand ideas, these theories that span from the quantum foam to the edge of the multiverse? We can't rerun the universe with different settings to see what happens. Or can we? This is where the power of modern supercomputers enters the story, allowing us to do the next best thing: build our own virtual universes from the ground up. Cosmological simulations are the ultimate cosmic sandbox, a digital playground where physicists can input the laws of nature, press play, and watch 13.8 billion years of cosmic history unfold in a matter of weeks. These aren't simple video game graphics. They are some of the most complex and computationally intensive calculations ever performed, involving billions of particles interacting through gravity, gas dynamics, and the subtle, pervasive influence of dark energy. Imagine the challenge. To create a realistic virtual cosmos, you need to simulate an almost unimaginable number of components. You start with a near-uniform grid representing the early universe, just after the Big Bang, seeded with the tiny density fluctuations we see in the cosmic microwave background. This grid is populated with billions of particles, each one representing a huge clump of dark matter, and another set of particles to track the ordinary gas that will eventually form stars and galaxies. Then you set the rules. You code in the known laws of physics, gravity, hydrodynamics, the chemistry of gas cooling and star formation, and crucially, you make a choice about dark energy. You set the value for its equation of state W. Is it exactly -1, a true cosmological constant? Or do you set it to -0.9 or -1.1 to simulate a dynamic quintessence or a phantom energy scenario? With all the parameters set, you unleash the awesome power of a supercomputer. Using incredibly complex algorithms, the machine calculates the gravitational pull between every one of those billions of particles, the pressure of the gas, the feedback from exploding stars, and the relentless push of dark energy as the simulation expands. It takes this initial, smooth state and lets it evolve, watching as gravity amplifies the tiny seeds into a vast cosmic web of filaments, voids, and halos of dark matter where galaxies are born. Iconic projects like the Millennium Simulation and the more recent Illustris TNG project have done precisely this, creating staggeringly detailed virtual universes that have become standard tools for cosmologists worldwide. The original Millennium Run, completed in 2005, tracked over 10 billion particles representing dark matter and gas in a cube of virtual space over 2 billion light-years on a side. For over a month, the supercomputer crunched the numbers, and the result was a breathtakingly realistic representation of the large-scale structure of the universe, complete with familiar-looking clusters, filaments, and voids. But its real power wasn't just in creating a pretty picture, it was in its utility. Researchers have used the Millennium database for thousands of studies, using it to interpret real telescope data and test theories of galaxy formation. The follow-up Illustris TNG project went even further, incorporating more sophisticated physics for star formation, supernova explosions, and the growth of supermassive black holes, resulting in simulated galaxies that uncannily resemble their real-world counterparts in size, shape, and distribution. The true genius of these virtual universes is their ability to run controlled experiments that are impossible in reality. Scientists can create a suite of simulations that are identical in every way except for one key variable, the nature of dark energy. They can run one universe with a cosmological constant and another where dark energy is a quintessence field that weakens over time. Then they can compare the results. How does the cosmic web differ? Do galaxy clusters form earlier or later? Is the distribution of galaxies slightly different? These subtle differences create a unique fingerprint for each dark energy model. When astronomers then go out and make real observations with telescopes like Euclid or Rubin, they can compare the actual universe to these different simulated versions. It's like having a set of reference fingerprints at a crime scene. By matching the real data to the simulated fingerprint, they can identify which model of dark energy best fits our reality. This process turns abstract theoretical equations into tangible, testable predictions about the structure we should see in the night sky. Furthermore, these simulations are indispensable for preparing for new observational data. Before a powerful new telescope like the Roman Space Telescope even opens its lens, scientists have already run thousands of simulations of what its data might look like under different scenarios. They use these mock datasets to develop and refine the complex computer algorithms needed to analyze the real observations, to understand the potential sources of error, and to forecast just how precisely they will be able to measure the properties of dark energy. In this way, cosmological simulations act as a crucial bridge, connecting the raw, theoretical mathematics of gravitation and field theory to the messy, complex, and beautiful reality of the universe we observe. They allow us to experiment with the very fabric of reality, offering a glimpse into alternate cosmic histories and futures, and providing our best hope for turning the profound mystery of dark energy into a solved equation. This concept of a finely tuned universe, where the value of dark energy seems perfectly calibrated for our existence, leads us down a path that is as philosophically profound as it is scientifically daring. It pushes us to consider a possibility that was once the sole domain of science fiction, the multiverse. Imagine for a moment that our cosmos, with its specific laws and constants, is not the only one. Picture instead a vast, perhaps infinite, ensemble of universes, a cosmic landscape where every possible variation of physical law is realized somewhere. In most of these universes, the constants are set to values that are utterly hostile to life. The strength of dark energy might be so immense that the universe tears itself apart in a fraction of a second before a single atom can form. Or it could be so weak and negative that the entire cosmos collapses back in on itself immediately after the Big Bang. But in an incomprehensibly tiny fraction of these universes, by pure random chance, the numbers come out just right. The dark energy value is minuscule but positive. Gravity is strong enough to form galaxies, but not so strong as to cause a rapid collapse. And the nuclear forces are perfectly balanced to forge the carbon in our bones and the oxygen in our lungs. In this multiverse scenario, the puzzling, exquisitely fine-tuned value we measure for dark energy is no longer a mysterious coincidence waiting for a unique explanation. It becomes a straightforward selection effect. We could not possibly find ourselves in a universe where the value is too high or too low, because those universes are dark, empty, or short-lived. We observe this specific value because it is the only type of value that allows for conscious observers like us to exist and ponder it. This line of reasoning is known as the anthropic principle, and it offers a breathtakingly elegant way to solve the fine-tuning problem. The universe isn't fine-tuned for us. We are simply the accidental product of its habitable parameters. This idea, however, is perhaps the most controversial in all of modern cosmology. For many physicists, the multiverse hypothesis feels like a retreat from the traditional goal of science, which is to find a unique, predictive, and testable theory that explains why the constants of nature must have the values they do. The most stinging criticism is that it appears to be untestable. If these other universes are forever beyond our observational horizon, causally disconnected from our own, then how can we ever verify their existence? A theory that can explain any possible outcome by invoking an infinite number of unobservable universes risks becoming unfalsifiable, and according to the philosopher Karl Popper, unfalsifiability is the line between science and pseudoscience. To its detractors, the multiverse can seem like a cop-out, a way to avoid the hard work of finding a deeper, more fundamental theory that naturally predicts the value we see. They argue it replaces physics with a form of metaphysics, a just-so story that explains everything and therefore nothing. Yet, for a growing number of theorists, particularly those working in string theory and quantum cosmology, the multiverse is not a choice. It is an inevitable consequence of our best mathematical attempts to understand reality. String theory, for instance, predicts not one unique universe, but a colossal landscape of possible universes, perhaps 10 to the 500th power of them, each with different physical laws determined by the way its extra dimensions are curled up. In this view, the multiverse isn't an add-on invented to solve the dark energy problem. It falls out naturally from the equations. From this perspective, not adopting a multiverse interpretation would be the unscientific act, as it would require ignoring a clear prediction of our most promising framework for a theory of everything. For these scientists, the anthropic principle is not a surrender. It is a practical tool for making predictions within a vast cosmos we are only beginning to comprehend. It shifts the question from why are the constants what they are to what are the conditional probabilities for observers like us within the multiverse. This is a question that, in principle, can be answered with mathematics and statistical reasoning. The debate ultimately forces us to confront the very nature of reality and the limits of scientific inquiry. Dark energy, this faint whisper from the vacuum, has become our gateway to these ultimate questions. It challenges us to consider whether the laws of physics we hold as universal and immutable are truly fundamental, or if they are merely local bylaws, a parochial set of rules that just happen to govern our particular cosmic neighborhood. This isn't just about astronomy. It's a profound inquiry into whether our universe is unique and somehow special, or if it is one unremarkable bubble in a frothing, infinite cosmic ocean. The multiverse hypothesis, for all its controversies, represents a bold attempt to grapple with the evidence before us. It expands the canvas of reality to a scale that is almost impossible to fathom, suggesting that the answer to the dark energy puzzle might not lie within our universe at all, but in the mind-bending architecture of a reality far grander than we ever dreamed. But with all this talk of phantom energies and cosmic rips, it's no wonder that dark energy has become a breeding ground for some pretty common misconceptions. Let's take a moment to clear the air and separate the solid science from the sci-fi speculation. Perhaps the most frequent mix-up is between dark energy and its similarly named cousin, dark matter. It's an easy mistake to make. They both have dark in their name, and we can't see either of them, but that's pretty much where the similarities end. Think of them as two completely different characters in the cosmic play. Dark matter is the builder. It's a form of matter, which means it has mass and exerts a gravitational pull. It's the invisible scaffolding that holds galaxies together, the glue that keeps stars from flying off into the void. Dark energy, on the other hand, is the disruptor. It's not matter at all, it's a property of space itself that creates a repulsive effect, pushing the universe apart. One pulls things together, the other pushes them apart. One is clumpy and gathers in halos around galaxies. The other is perfectly smooth and uniform everywhere. They are two distinct mysteries with two very different roles. Another popular idea is that dark energy is a form of anti-gravity. This sounds catchy, but it's not quite accurate. In science fiction, anti-gravity often means something that locally cancels or reverses gravity, like a device that lets a spaceship float. Dark energy doesn't work like that. It doesn't create a shield against gravity in a specific place. Instead, its effect is global and woven into the fabric of spacetime. A better way to think about it is through Einstein's theory of general relativity, which tells us that the curvature of spacetime, what we experience as gravity, is determined by both the energy and the pressure of the contents of the universe. Normal matter and dark matter have positive energy density and negligible pressure, so they curve spacetime in a way that attracts. Dark energy has a weird property. It has a strong negative pressure. According to Einstein's equations, this negative pressure actually contributes to gravity, but in a repulsive way. So it's not anti-gravity. It's a consequence of gravity itself when it has to deal with this strange form of energy. It's gravity working in reverse on the largest scales because of the specific properties of the vacuum. Then there's the concern that dark energy might violate the fundamental law of energy conservation, which states that energy cannot be created or destroyed, only transformed. If the universe is expanding and the density of dark energy remains constant, that means the total amount of dark energy in the universe is increasing as new space is created. This seems to break the rule. However, this is only a problem if we consider the universe as a closed system in the way we traditionally think about it. In the context of general relativity and an expanding universe, the law of energy conservation becomes more nuanced. In an expanding space-time, energy conservation is not guaranteed in the same simple way it is in a static, flat space. The energy associated with the gravitational field can be tricky to define globally. So, while it seems counterintuitive, the increasing total energy of dark energy is not a violation of our current physical laws. It's a fascinating feature of how those laws operate on a cosmic scale. The energy is essentially being borrowed from the gravitational field of the expanding universe itself. It's also vital to remember that dark energy is primarily a label for our ignorance. It's not the name of a discovered particle or a confirmed force. It is a placeholder term for whatever is causing the observed acceleration of the universe's expansion. We see the effect the galaxies flying apart faster and faster, and we have to call that something. Dark energy is that something. Its discovery wasn't a wild guess or speculative fantasy. It was a conclusion forced upon us by overwhelming, reproducible evidence from independent lines of inquiry. The dimming of distant supernova, the patterns in the cosmic microwave background, the baryon acoustic oscillations, they all tell the same story. Scientists didn't want the universe to be accelerating. They were trying to measure how much it was slowing down. The data was so shocking that the team spent months trying to disprove their own results, searching for any possible error. The evidence had to be rock solid to overturn the established model of the cosmos. This process is the very heart of good science, following the data wherever it leads, even if it leads to a profoundly strange and unexpected place. To make this abstract concept a bit more tangible, imagine space as a stretchy rubber sheet, which is a common analogy for spacetime. Now, imagine that this rubber sheet isn't passive. It has a tiny amount of energy embedded within every single square centimeter of it. This is the energy of the vacuum, the cosmological constant. As the universe expands, it's like we're stretching this rubber sheet. When you stretch rubber, you put energy into it. That energy is stored as potential energy in the stretched material. In our cosmic analogy, as more space is created, more of this innate vacuum energy comes into existence, and it drives the stretching to go even faster. The rubber sheet isn't just expanding, it's self-replicating and accelerating its own expansion because the very act of stretching adds more of the energy that causes the stretching. This feedback loop is what makes the acceleration so relentless and what distinguishes dark energy from any simple explosive force from the past. It's a feature of the stage itself, not the actors on it. Clearing up these misconceptions isn't just about scientific pedantry, it's about building a foundation of public understanding. When people have a clear and accurate picture of what we know and what we're still figuring out, their excitement for new discoveries is rooted in reality, not confusion. This creates a more engaged and informed audience, one that can truly appreciate the profound mystery that scientists are working so hard to solve. Yet this cosmic humility is not a call to despair, but an invitation to a deeper, more profound curiosity. The very act of investigating dark energy, of devoting immense resources and human intellect to unraveling a mystery that offers no immediate practical benefit, is a powerful testament to who we are as a species. We are not content to simply exist within this universe. We are driven to understand it, to decode its deepest laws, even when those laws are hidden in the void itself. This pursuit is a fundamental expression of the human spirit, a declaration that our purpose extends beyond survival and comfort. It is about the innate need to know, to explore, and to find our place within the grand narrative of existence. The billions of dollars and decades of work invested in projects like the Euclid Telescope or the Vera Rubin Observatory are not just an investment in astronomy. They are an investment in human potential, in our relentless drive to push the boundaries of knowledge and see just a little further into the unknown. This endeavor connects us to every earlier generation that ever looked up at the night sky in wonder, from the builders of ancient observatories to the philosophers who first pondered the nature of the stars. We are continuing that timeless conversation, armed with better tools but fueled by the same essential spark of curiosity. This raises a vital question about value. What is the worth of knowledge for its own sake? In a world facing urgent, immediate problems, some might argue that such abstract cosmological research is a luxury we cannot afford. But this perspective misses the profound, albeit indirect, ways that fundamental science enriches our world. The struggle to detect the faint whisper of dark energy has driven monumental advancements in technology, from the development of exquisitely sensitive digital camera sensors that now benefit medical imaging, to the creation of powerful data analysis algorithms that filter through noise in countless other fields. More importantly, it provides something less tangible but equally crucial. It inspires awe. The story of dark energy, of a universe far stranger and more wonderful than we ever imagined, captures the public imagination. It draws young minds into the fold of science and technology, fostering the next generation of engineers, programmers, and critical thinkers who will tackle the world's problems with a broader perspective. It reminds us that our world is part of a much larger, dynamic, and evolving cosmos, fostering a sense of global citizenship and a humbling awareness that we share a single, fragile planet adrift in a vast and mysterious sea. The value of this research is not measured just in patents or spin-off technologies, but in the expansion of human consciousness itself. Ultimately, the quest to decode dark energy transcends the field of physics and enters the realm of philosophy and meaning. It forces us to confront the most fundamental questions about reality and our role within it. Are the laws of physics unique and inevitable, or are we, as the anthropic principle suggests, simply living in one rare universe among a multiverse where the constants are just right for life? Does the universe have a purpose or a destiny, or is its future simply the cold, mechanical outcome of a dominant, repulsive energy? We may never have definitive answers to these questions, but the act of asking them, of using observation, reason, and collaboration to probe the edges of understanding, is what defines our humanity. Dark energy, this invisible, dominant force, has become our modern sphinx, presenting us with a riddle that challenges our intellect and our identity. In seeking to answer it, we are not just learning about the cosmos, we are learning about ourselves, about our capacity for wonder, our resilience in the face of the unknown, and our eternal desire to find meaning in the magnificent, accelerating darkness. But the quest to understand dark energy does not exist in an isolated bubble of astronomy. Its gravitational pull extends far beyond, drawing in experts from seemingly unrelated fields and creating a vibrant, interdisciplinary conversation that is reshaping the boundaries of modern science. This mystery acts as a powerful catalyst, forcing physicists, mathematicians, and even philosophers to pool their knowledge and tools, proving that the biggest questions about the cosmos cannot be answered by a single discipline working alone. The most natural and profound collaboration is with particle physics, and it's a partnership born from a shared frustration, the cosmological constant problem. The vacuum energy predicted by quantum field theory is catastrophically larger than the dark energy we observe, creating a chasm of 120 orders of magnitude between expectation and reality. This isn't just a small accounting error, it's a fundamental crisis that suggests a deep flaw in our understanding of how the quantum world of the incredibly small connects to the cosmic world of the incredibly large. Particle physicists who specialize in the behavior of subatomic particles and forces are now forced to consider the cosmological consequences of their theories. Are there undiscovered particles or symmetries like supersymmetry that could cancel out this vacuum energy to the precise, tiny level we see? Or does this discrepancy point toward a more radical need for a theory of quantum gravity, a framework that can seamlessly unite the rules governing quarks with the rules governing quasars? The dark energy problem has become a crucial experimental test for theories that were once purely mathematical abstractions, grounding them in the observable reality of an expanding universe. This drive toward unification naturally pulls in the field of mathematics, which provides the essential language and tools to build these new models. Concepts from differential geometry, used to describe the curvature of space-time in general relativity, now mingle with the complex topology of extra dimensions proposed by string theory. The equations governing hypothetical dark energy fields like quintessence are not simple. They are complex differential equations that require advanced numerical methods and new mathematical insights to solve. When cosmologists run massive computer simulations to model the influence of different dark energy models on the growth of the cosmic web, they are employing sophisticated algorithms from applied mathematics and statistics to analyze the results. The need to extract a faint signal from immense datasets, like the subtle distortion of galaxy shapes from weak gravitational lensing, pushes the boundaries of data science, leading to the development of powerful new statistical techniques and machine learning algorithms that can find patterns in the noise. These mathematical innovations, forged in the fire of cosmological inquiry, often find applications in other fields, from medical imaging to financial modeling, creating a feedback loop of intellectual progress. Perhaps most surprisingly, dark energy has reignited age-old questions in philosophy, particularly around the anthropic principle and the nature of existence. The staggering fine-tuning of the dark energy value, a number so precise that even a slight change would render the universe lifeless, forces us to confront why the cosmos appears so hospitable to observers like us. This leads directly into the realm of metaphysics and the controversial multiverse hypothesis. Philosophers of science are deeply engaged in debating the validity of these ideas. Is the multiverse a legitimate scientific concept, or is it an untestable metaphysical speculation? What does it mean for our understanding of science if the fundamental constants of nature are not necessary laws, but simply random, local outcomes in a vast cosmic landscape? These are not questions with easy answers, but they are essential ones that push against the very definition of what science can and should explain. The dark energy problem holds up a mirror to our own limitations, challenging us to consider whether we are uncovering the universe's unique blueprint or simply describing the bylaws of our own particular cosmic neighborhood. This fusion of disciplines is not just theoretical, it is embodied in the very structure of modern research teams. A project like the Dark Energy Survey or the Euclid mission is not staffed solely by astronomers. The collaboration includes particle physicists who contribute their expertise in detector technology and statistical analysis, computer scientists who build the infrastructure to process petabytes of data, and mathematicians who develop the algorithms to interpret it. String theorists work with cosmologists to build concrete models of how their abstract landscape of vacua might manifest in the observable universe, making specific, testable predictions that future telescopes can probe. This cross-pollination of ideas is where true breakthroughs often occur. A technique developed in one field can solve a stubborn problem in another, and a perspective from an outside discipline can shatter a long-held assumption. Dark energy, in its utter mysteriousness, has become a nexus for this kind of intellectual exchange, a common puzzle that requires every tool in our intellectual toolbox to solve. It demonstrates that the most profound mysteries of the universe are not the property of any single branch of knowledge, but are instead shared challenges that require the collective brilliance of the human mind to decode. But how do you translate these mind-bending concepts from the frontiers of theoretical physics into something that a high school student, a curious retiree, or anyone without a PhD can grasp and feel excited by? This is the vital mission of educational outreach, a field dedicated to building bridges between the complex universe of professional cosmology and the public's innate sense of wonder. The challenge is significant. You can't hand someone a textbook full of tensor calculus and expect their eyes to light up. Instead, educators and science communicators have become masters of the analogy, the visualization, and the hands-on experience, finding creative ways to make the invisible not just visible, but tangible and thrilling. One of the most powerful tools in this arsenal is the use of simple, relatable analogies that anchor an abstract idea in everyday experience. To explain the accelerating expansion driven by dark energy, a common and effective analogy is that of a loaf of raisin bread baking in an oven. Imagine the dough represents the fabric of space and the raisins are galaxies. As the bread bakes and rises, the dough itself expands. From the perspective of any single raisin, all the other raisins are moving away. And crucially, the farther away a raisin is, the faster it appears to be receding, because there's more expanding dough between you and it. Now, to add dark energy to the mix, you'd have to imagine that the yeast in the bread suddenly gets more active as the bread gets bigger, causing the loaf to rise faster and faster over time. This simple kitchen scenario captures the essence of the Hubble expansion and the puzzling acceleration in a way that is immediately intuitive, providing a mental model that anyone can carry with them. For those who learn best by seeing, planetariums offer an unparalleled immersive experience. Modern digital planetarium systems are far more than just star projectors. They are powerful simulation engines capable of flying audiences through a realistic model of the entire observable universe. A well-crafted planetarium show about dark energy might begin by zooming in on the familiar constellations before pulling back at a breathtaking pace, out past the planets, past the stars of our galaxy, and into the deep void where galaxies themselves become points of light. The show can then visualize the key evidence, perhaps by highlighting the specific supernova that revealed the acceleration, showing their actual location in the cosmos and demonstrating how their unexpected dimness was the crucial clue. It can animate the concept of baryon acoustic oscillations, making the frozen sound waves of the early universe visible as a faint, shimmering grid underlying the distribution of galaxies. In the comfortable darkness of the dome, surrounded by these cosmic visuals, the abstract becomes awe-inspiring, transforming data points into a profound sensory experience that conveys the scale and mystery of the cosmos in a way a lecture never could. The digital age has also democratized access to these tools through online simulations and interactive websites. Platforms like the World-Wide Telescope, developed by Microsoft, or ESA's Gaia Sky, allow anyone with a computer to become a virtual astronomer, exploring vast datasets and flying through three-dimensional maps of the universe. For a more hands-on approach, citizen science projects are a revolutionary way to engage the public. Platforms like Zooniverse host projects where volunteers can contribute to real scientific research. Imagine a project where participants are shown images of distant galaxies and asked to help classify their shapes. This isn't just a game. This is the same data that professional astronomers use to study how dark matter and dark energy influence galaxy formation. By participating, a person is not just learning about science. They are actively doing it, becoming part of the global effort to decode the universe's secrets. This sense of contribution is incredibly powerful, transforming a passive viewer into an active participant in the grand scientific story. The importance of this work extends far beyond simply sharing fun facts about the cosmos. At its heart, it is about fostering a fundamental scientific literacy that is essential for modern society. We live in a world increasingly shaped by science and technology, where complex issues like climate change, artificial intelligence, and public health require a citizenry that can think critically, evaluate evidence, and understand the basic process of scientific inquiry. By demystifying a topic as complex and counterintuitive as dark energy, we are not just teaching people about astronomy, we are giving them a masterclass in how science works. We show them how a startling observation leads to a hypothesis, how that hypothesis is tested with multiple, independent lines of evidence, and how our understanding evolves over time, even if it means overturning cherished ideas. This builds a resilience against misinformation and a deeper appreciation for the painstaking, collaborative, and self-correcting nature of the scientific endeavor. Ultimately, the goal is to inspire. For every child who visits a planetarium and looks up with wide-eyed wonder, for every adult who spends an evening classifying galaxies online, there is the potential to ignite a spark of lifelong curiosity. That spark might lead a student to pursue a career in STEM, becoming the next generation of scientists who will finally solve the dark energy puzzle. But even for those whose paths lead elsewhere, that spark matters. It creates a more informed and engaged public, one that values fundamental research and supports the funding for great telescopes and space missions. It reminds us all that the universe is a place of breathtaking mystery and beauty, and that we all have a place in it. By making the cosmos accessible, we empower everyone to look up at the night sky and not feel small or confused but connected, to the scientists, to the history of discovery, and to the ongoing, glorious effort to understand our incredible universe. After years of meticulous observation and analysis, the Dark Energy Survey finally began to unveil its results, offering the most comprehensive view of dark energy's influence to date. This monumental project, which wrapped up observations in 2019 after scanning 1/8 of the night sky over 570 nights, wasn't just about collecting data. It was about building an ironclad case, using 3 independent lines of evidence to corner the same cosmic suspect. The survey's powerful 570-megapixel dark energy camera, mounted on the Blanco telescope in Chile, acted as a cosmic cartographer, painstakingly charting the positions, shapes, and distances of over 300 million galaxies. This immense catalog provided the raw material for all 3 of its primary investigative techniques: weak gravitational lensing, baryon acoustic oscillations, and the study of Type Ia supernova. By wielding all these tools simultaneously, DS embodied the modern scientific principle of cross-validation, ensuring that any conclusion drawn wasn't an artifact of a single method, but a consistent truth emerging from multiple angles. The most compelling story to emerge from this mountain of data was the consistent, tight constraint it placed on the equation of state parameter, W. When the final cosmological results were combined, they pointed to a value incredibly close to -1, precisely what you would expect if dark energy were indeed Einstein's cosmological constant, a steady, unchanging feature of the vacuum of space. The weak lensing measurements, which mapped the invisible dark matter by seeing how it warped the light from distant galaxies, told a story of cosmic structure growth that had been subtly suppressed over time, just as a constant dark energy would predict. Simultaneously, the pattern of baryon acoustic oscillations, the fossilized imprint of ancient sound waves in the distribution of galaxies, provided a precise ruler that confirmed the expansion history. Even the survey's catalog of Type Ia supernova, though smaller than those from dedicated supernova searches, added another layer of confirmation, showing the acceleration in action. The beauty of the DS results wasn't that one technique was perfect, but that all 3, despite their completely different sources of potential error, were all singing the same tune in harmony, a powerful chorus in favor of the simplest model. Yet, for all its precision, the Dark Energy Survey did not slam the door shut on more exotic possibilities. The data, with its tiny error bars, still left a sliver of room for dynamics. The combined results did not demand that W be exactly -1. They were perfectly consistent with it being, for example, -0.97 or -1.01. This tiny window of uncertainty is where the remaining scientific drama resides. It means that while the cosmological constant is an excellent fit to the data, the survey couldn't definitively rule out some forms of quintessence theoretical models where dark energy strength could evolve over time. This isn't a failure, it's a reflection of just how subtle these effects are to measure. Teasing apart the difference between a perfectly static vacuum energy and a slowly evolving field requires a level of precision that was simply beyond the reach of even this ambitious survey. DS set a new standard, but it also clearly mapped the path for its successors, showing them exactly how much further they needed to go. A huge part of the DS legacy lies not just in the final numbers, but in its heroic battle against systematic errors, the hidden biases that can secretly undermine any grand astronomical measurement. Imagine trying to measure the microscopic distortion of a galaxy's shape from billions of light years away, but your own telescope's optics, the Earth's atmosphere, and even the delicate physics of the camera's sensors all introduce their own tiny distortions that can mimic the cosmic signal you're desperately seeking. The DS team spent years characterizing these effects with obsessive detail. They took images of star fields to map every possible optical imperfection in their telescope and camera. They developed incredibly sophisticated software to model how their sensors converted light into digital signals, correcting for any artifacts. They even used advanced image simulations, creating mock universes with known properties, to test their entire analysis pipeline from start to finish. This painstaking work to understand and eliminate their own instrumental biases is what gave the final results their rock-solid credibility. It transformed a fascinating observation into a trustworthy measurement, showcasing the unglamorous but utterly essential groundwork that underpins all modern cosmology. The Dark Energy Survey stands as a towering testament to what large-scale international collaboration can achieve. It wasn't the work of a lone genius, but of over 400 scientists from 25 institutions across 7 countries. This collective effort was essential to tackle a problem of such immense scale, requiring astrophysicists, particle physicists, statisticians, and computer scientists to all work in concert. The survey produced over 50 terabytes of raw data, which then had to be processed, calibrated, and analyzed, a task that required a global network of supercomputers and years of effort. This model of big science, where progress is measured in incremental steps of increasing precision built upon the work of hundreds, is the new paradigm for decoding the universe's deepest secrets. DS didn't claim to have solved the mystery of dark energy. Its greater victory was in rigorously narrowing the possibilities and proving the effectiveness of its multi-pronged approach. It handed the baton to the next generation of missions like Euclid and the Rubin Observatory, having shown them where to look and how to see more clearly than ever before. Yet, just as we were building this seemingly consistent picture of the cosmos, a troubling crack began to appear in the foundation, a discrepancy so persistent it has grown into a full-blown crisis in cosmology known as the Hubble Tension. This isn't a minor quibble over decimal points. It's a fundamental disagreement about how fast the universe is expanding right now, and it threatens to upend our most cherished models. The story starts with 2 completely different methods for measuring the Hubble constant, denoted as h0, which represents the current expansion rate of the universe. One method looks at the ancient universe, the other at the relatively modern one. The shocking part is that these 2 methods, both exquisitely precise and rigorously tested, are giving us 2 different answers that stubbornly refuse to agree. The first method uses the cosmic microwave background as its anchor. The Planck satellite, which mapped the CMB in stunning detail, allows cosmologists to take a snapshot of the infant universe and then run the cosmic movie forward using the standard lambda CDM model. This model includes the known amounts of dark matter and dark energy and the equations of general relativity. When you press play on this simulation, it predicts what the expansion rate should be today. This is a model-dependent measurement, but it's incredibly precise. The Planck data gives a value for the Hubble constant of about 67.4 kilometers per second per megaparsec. This means that for every megaparsec of distance, a megaparsec is about 3.26 million light-years. A galaxy is moving away from us at 67.4 kilometers per second faster. The second method takes a much more direct route, measuring the expansion rate using what astronomers call the distance ladder. This is a meticulous, step-by-step process that builds out from our local cosmic neighborhood. The first rung on the ladder involves using parallax to measure the distances to nearby stars with incredible accuracy. The next rung uses those known distances to calibrate the brightness of certain types of stars like Cepheids variables in slightly more distant galaxies. Cepheids are crucial because they pulsate at a rate that is directly tied to their true brightness, making them standard candles. Finally, Astronomers use those Cepheids in galaxies that also host type Ia supernova to calibrate the immense brightness of those supernova. Once calibrated, these supernova can be seen across billions of light years, allowing for a direct measurement of how fast the universe is expanding today. This entire process is complex and painstaking, but it is largely model-independent. It's a direct measurement of the contemporary cosmos. The teams doing this work, led by astronomers like Adam Rees, have relentlessly refined their techniques, accounting for every possible source of error. And their result is unequivocal. The universe is expanding at about 73 kilometers per second per megaparsec. The problem is immediately obvious. 67.4 and 73 are not the same number. There is a discrepancy of about 5 to 6 kilometers per second per megaparsec between the early universe measurement and the late universe measurement. This might sound like a small difference, but the precision of each measurement is so high that the error bars do not overlap. This isn't a case of sloppy science. It's a case of two impeccable lines of evidence pointing in two different directions. This is the Hubble tension, and it has now persisted for over a decade, surviving countless re-examinations and attempts to find a hidden systematic error in either method. The longer it persists, the more likely it becomes that it's not an error at all, but a sign of new physics, a clue that our standard model of cosmology, for all its success, is incomplete. So what could this new physics be? If the tension is real, it means that the universe today is expanding faster than our model, based on the early universe, predicted it should. Something must be giving it an extra kick. This is where the connection to dark energy becomes electrifying. Perhaps dark energy isn't a simple cosmological constant after all. Maybe it's a dynamic field like quintessence that is evolving and changing in strength. If this field began to act more strongly over the last several billion years, it could provide that additional push needed to explain the higher expansion rate we measure locally. Alternatively, the issue might not be with dark energy itself, but with dark matter. Maybe dark matter has properties we haven't yet accounted for. Perhaps it can interact with itself or with light in a very subtle way that changes how structures form and how the expansion evolves. Other, even more exotic ideas are on the table. Could it be that we are seeing the first evidence for a new type of relativistic particle that flooded the early universe and changed its expansion history? Or perhaps the properties of dark energy are not uniform, and we live in a local void that is expanding slightly faster than the cosmic average, though this is considered a less likely explanation. The profound implication of the Hubble tension is that it reveals cosmology as a living, breathing science, not a settled doctrine. It's a powerful reminder that anomalies are not nuisances to be smoothed over. They are the guideposts to deeper understanding. For centuries, scientific progress has been driven by the tiny details that don't quite fit, the observations that refuse to conform to our elegant theories. The Hubble tension is exactly that kind of detail. It forces cosmologists to question their assumptions, to double-check their work, and to dream up new, more creative models of the cosmos. It ensures that the field remains dynamic and exciting, a frontier where the biggest questions are still very much up for grabs. This discrepancy tells us that dark energy might not be a standalone puzzle to be solved, but one piece of a much larger, more complex picture that we are only beginning to glimpse. The pieces of the cosmic puzzle are all on the table, but the Hubble tension suggests that the picture on the box might be wrong, and we may need to consider a completely new image to make them all fit together. This idea of a universe that can suddenly and violently accelerate its own expansion might sound eerily familiar, and for good reason. We've actually seen this movie before, or rather, we've seen the incredible sequel. The stunning discovery of dark energy-driven acceleration in the modern universe is a cosmic echo of an even more dramatic event that occurred at the very dawn of time: cosmic inflation. For a fleeting fraction of a second after the Big Bang, the universe is believed to have undergone an exponential growth spurt, ballooning from a subatomic speck to something approaching the size of a grapefruit faster than the speed of light. This wasn't expansion, it was a runaway stretching of spacetime itself, and it was driven by a mechanism that looks suspiciously similar to what we call dark energy today. Both phenomena are episodes of accelerated expansion, and both are thought to be powered by a peculiar type of field that imbues the vacuum of space with a powerful negative pressure. It's as if the universe has a favorite tool for radical change, pulling it out of its toolbox once to create everything and then again, billions of years later, to dictate how everything will end. The engine behind the inflationary epoch is theorized to be a field dubbed the inflaton. Think of this not as a particle, but as a kind of energy field that temporarily got stuck in a high-energy state, like a ball perched at the top of a hill. This state had a crucial property. Its energy density was incredibly high, and it exerted a tremendous negative pressure. According to Einstein's equations, this combination generates a powerful repulsive gravity, which is what blew up the universe so spectacularly. As the inflaton field slowly rolled down its energy hill, it eventually reached the bottom, and its energy decayed into the hot soup of particles that would eventually form atoms, stars, and us. Inflation shut off, and the universe settled into the more sedate, gravity-dominated expansion we discussed earlier. Now, fast forward nearly 14 billion years. We see acceleration again, but this time it's weak, feeble, and constant. If dark energy is indeed a cosmological constant, it's like a ghostly, diluted remnant of that incredible inflationary power, a faint afterglow of repulsion that never turned off. If it's quintessence, it's more like a distant cousin of the inflaton, a different field that is only now awakening and beginning to gently push, rather than shove, the universe apart. This profound connection invites a tantalizing question. Are inflation and dark energy two manifestations of the same underlying physics? Could the same fundamental mechanism that crafted the large-scale smoothness of the cosmos also be responsible for its ultimate fate? For theoretical physicists, this is a siren call. It suggests the possibility of a unified theory of cosmic acceleration, a single framework that can explain both the universe's explosive birth and its accelerating old age. Perhaps the inflaton field didn't completely disappear. Maybe it decayed into a much weaker form that has been lying dormant, and that residual energy is what we're now measuring as the cosmological constant. Or perhaps the universe contains many such fields, and the inflaton was just the first to act. Quintessence could be another one, stirring to life only after the universe had expanded and cooled to a specific point. Exploring these links is like finding two seemingly different crimes were committed with the same unique weapon. It forces you to consider that they might be connected, and that solving one could provide the crucial clue to solving the other. Studying the detailed properties of dark energy today could therefore provide a unique window into the highest energies of the early universe, energies so extreme we could never hope to recreate them in a particle collider. The precise value of the dark energy density, and whether it is truly constant or dynamic, could tell us something about the shape of that original inflaton energy hill, its steepness and height. Conversely, the stunningly precise measurements of the cosmic microwave background, which is the direct remnant of the end of inflation, place incredibly tight constraints on what any dark energy model must look like. A theory that tries to unify inflation and dark energy must successfully predict the patterns we see in that ancient light, while also matching the observed acceleration we measure today. This is a brutally difficult challenge, but it's one that could ultimately lead us to a deeper understanding of why the universe is the way it is, weaving its entire history from the first instant to the last into a single, coherent story. It suggests that acceleration isn't a bizarre anomaly. It's a fundamental part of the cosmic cycle, a recurring theme written into the very laws of physics that governs the most transformative chapters in the life of the universe. While we often focus on the giants of cosmology, dark energy and dark matter, there exists a cast of subtle, elusive particles that, despite their faint presence, play a crucial role in fine-tuning our cosmic models. Among these, neutrinos stand out as ghostly messengers from the early universe, and their behavior might hold indirect clues to the larger mystery of acceleration. These particles are among the most abundant in the cosmos, yet they are famously aloof, interacting with normal matter only through the weak nuclear force and gravity, allowing trillions to pass through your body every second without a trace. In the grand inventory of the universe, their total mass is minuscule compared to dark matter or dark energy, but their influence is far from negligible. They were born in the fiery first second after the Big Bang, and they have been streaming through the cosmos ever since, their properties subtly encoded in the large-scale structure we observe today. Because they travel at near light speed for much of cosmic history, they act like a kind of cosmic radiation, their energy and pressure influencing how structures form in their wake. The key connection to dark energy lies in this very interplay between neutrinos and the growth of cosmic structure. Imagine the universe as it's evolving. Dark matter's gravity is pulling matter together to form the cosmic web, while dark energy is working against this, stretching space and suppressing the clumping of matter. Neutrinos add a fascinating third actor to this tug-of-war. For most of the universe's history, they were relativistic, meaning they zipped around at speeds so high that they could easily escape the gravitational pull of emerging dark matter halos. This smooths things out. As these fast-moving neutrinos stream out of denser regions, they carry energy away, effectively acting as a drag on the growth of the very largest structures. The timing and scale of this effect depend critically on the neutrino's mass. Heavier neutrinos would have slowed down earlier in cosmic history, transitioning from behaving like radiation to behaving more like matter, and thus starting to clump under gravity later on. This leaves a specific imprint on the distribution of galaxies and clusters, an imprint that telescopes can hunt for. This is where cosmology becomes a breathtaking exercise in precision accounting. When scientists analyze the data from the cosmic microwave background or from galaxy surveys, they are building a model that includes every known component: ordinary matter, dark energy, and radiation, which includes photons and neutrinos. If they get the properties of one component wrong, it throws off the fit for everything else. For instance, if we were to inaccurately estimate the total mass of neutrinos, it would create a mismatch between the observed amount of structure in the universe and the predicted amount based on the Planck CMB data. This discrepancy could then be mistakenly interpreted as a sign that dark energy is behaving differently than a simple cosmological constant. A dynamic form of dark energy, like quintessence, suppresses structure growth in a specific way over time. An error in the neutrino mass could mimic that specific suppression pattern, leading us down a false path. Therefore, to isolate the true fingerprint of dark energy's nature, we must first pin down the properties of these tiny particles with exquisite precision. They are a source of background noise in our cosmic signal, and we need to subtract their effect perfectly to hear the true whisper of dark energy. The quest to measure neutrino mass is thus not a side project. it is a central campaign in the war on cosmic uncertainty. Particle physics experiments on Earth have determined that neutrinos must have mass, but they can only measure the differences between the masses of the three neutrino types, not the absolute mass scale. This is where cosmology provides a powerful, independent tool. By studying the large-scale structure of the universe and the precise patterns in the CMB, cosmologists can measure the sum of the masses of all neutrino species. Current constraints from the Planck satellite and other probes tell us that this sum is incredibly small, certainly less than 0.12 electron volts. To put that in perspective, that's more than 1,000,000 times lighter than an electron. This incredibly tiny mass has a correspondingly tiny but measurable effect on the cosmos. Next-generation telescopes like the Vera-C, Rubin Observatory and the Euclid Space Mission are designed to map the cosmic web in such detail that they will be able to measure this neutrino mass sum with definitive precision, potentially even detecting the exact moment in cosmic history when these particles slowed down and began to cluster. This will remove a major source of uncertainty, sharpening our view of dark energy's true impact. Beyond neutrinos, other relics from the early universe, like hypothetical actions or other light particles, could also be lurking in the background, their presence subtly altering the expansion history or the growth of structure. The beauty of modern cosmology is its holistic nature. It forces us to consider the entire cast of characters, from the most dominant forces to the most feeble particles. Every component, no matter how insignificant it seems, must be accounted for in our equations. A discrepancy between our model and our observations could be a sign of new physics related to dark energy, or it could simply be that we have miscalculated the contribution of a known but elusive particle. By relentlessly pursuing the properties of these minor players, we are effectively cleaning our cosmic lenses, ensuring that when we finally claim to see a deviation from the cosmological constant, it is a real discovery and not just dust on the telescope. The path to decoding the universe's greatest secret is paved with the meticulous study of its smallest inhabitants. While scientists grapple with equations and telescope data, the enigmatic concept of dark energy has escaped the confines of academic journals and ignited the imagination of storytellers, becoming a powerful narrative device across movies, video games, and literature. It often serves as a convenient stand-in for the ultimate unknown, a mysterious force that can be harnessed for fantastic technologies or one that threatens to unravel reality itself. In the realm of science fiction, dark energy is rarely portrayed with scientific accuracy. Instead, it's molded into a plot engine that can power faster than light travel, create universe-ending weapons, or grant god-like abilities. A prime example is the iconic Mass Effect video game series, where Element Zero and its generated Mass Effect fields are a clear allegory for dark energy, manipulated to reduce the mass of objects and allow for interstellar travel and incredible biotic powers. This creative liberty transforms a complex cosmological concept into an accessible and thrilling game mechanic, introducing millions of players to the term, if not the precise physics. These dramatic portrayals, while fictional, play a crucial role in shaping public perception and fueling curiosity. When a blockbuster film depicts heroes channeling dark energy to save the galaxy, it plants a seed in the audience's mind. It transforms an abstract scientific mystery into something tangible and consequential, something that could, in theory, be touched and used. This can be a double-edged sword. On one hand, it generates widespread excitement and a baseline awareness of cutting-edge science, potentially inspiring the next generation of physicists. On the other hand, it can create significant misconceptions, blurring the lines between theoretical physics and pure fantasy. the public might walk away with the idea that dark energy is a glowing substance you can collect in a jar, rather than a property of empty space itself. This places a greater responsibility on scientists and educators to engage with pop culture, using these fictional references as a gateway to explain the real, and in many ways even more fascinating, science behind the spectacle. The deep appeal of dark energy to storytellers is not hard to decipher. It represents the final frontier of human ignorance, the largest and most profound mystery we have yet to solve. It taps into fundamental human themes of exploration, the struggle against unknowable forces, and the existential question of our place in the cosmos. A force that dictates the fate of everything is the perfect backdrop for stories about hope, hubris, and humility. It allows writers to explore apocalyptic scenarios like the aforementioned Big Rip in a way that feels grounded in real scientific speculation, giving their stories a chilling layer of plausibility. Conversely, it can fuel optimistic tales of discovery and unity, where overcoming a cosmic threat requires the entire human race to work together. Dark energy, in its purest form, is a blank canvas onto which we project our deepest fears about cosmic insignificance and our highest hopes for transcendent understanding. This cultural exchange between science and fiction is a symbiotic relationship that stretches back centuries. Science provides the tantalizing, mind-bending concepts that fuel the creative fire of artists and writers. In return, these cultural works generate public support and fascination that helps justify the funding for major scientific endeavors. A teenager who first hears about dark energy in a comic book might be the one who goes on to design a key instrument for a future space telescope. The stories we tell about the universe, however inaccurate in their details, are a testament to our innate desire to make sense of the unknown. They reflect a collective yearning to personify the impersonal forces of nature, to find narrative and meaning in the cold, hard equations of physics. By analyzing how dark energy is used in pop culture, we aren't just critiquing its scientific merits, we are holding a mirror up to society, seeing what our current greatest mystery says about our contemporary hopes, anxieties, and the timeless human drive to tell stories about the stars. Now let's shift our gaze from the theoretical to the intensely practical, to the immense human and financial machinery that makes this cosmic quest possible. Unraveling the universe's deepest secret is, perhaps unsurprisingly, an extraordinarily expensive endeavor. The search for dark energy is not conducted by a lone astronomer peering through a telescope. It is a monumental, global enterprise involving billions of dollars, decades of work, and the coordinated effort of thousands of scientists, engineers, and technicians from dozens of countries. Projects like the Dark Energy Survey, the Euclid Space Telescope, the Vera-C, Rubin Observatory, and the Nancy Grace Roman Space Telescope represent some of the largest and most complex scientific collaborations ever assembled. The scale is almost hard to fathom. The Rubin Observatory alone carries a price tag of over $1.8 billion. The Euclid mission cost well over €1 billion. When you add up the funding from space agencies, national science foundations, and international partners across the globe, the total investment in probing dark energy runs into the many billions. This isn't just science, it's big science on a staggering scale, a testament to our species' collective will to understand its place in the cosmos. Such vast expenditures inevitably invite a critical and entirely valid question. Why, in a world grappling with poverty, disease, and climate change, what justifies channeling such immense resources toward an abstract puzzle billions of light years away? The justification is multi-layered, extending far beyond the simple answer of curiosity. First and foremost, there is the powerful argument of technological spin-offs. The challenges of building these cosmic observatories force us to invent new technologies that inevitably filter down into the broader economy, improving our daily lives. To build the dark energy camera, scientists had to develop digital sensors of unprecedented sensitivity and size. Those advancements now drive progress in medical imaging, from more detailed X-rays to early cancer detection systems. The immense data streams from these projects, petabytes of information that need to be stored, processed, and analyzed, have driven innovations in cloud computing, big data management, and machine learning algorithms. The same code used to find a subtle gravitational lensing signal in a galaxy image might later be used to improve facial recognition software or optimize global logistics networks. The precise optics required to focus the light of distant supernova push the boundaries of material science and engineering, leading to better lenses for everything from smartphones to surgical microscopes. The pursuit of fundamental knowledge, it turns out, is a powerful engine for practical innovation. Beyond the technological bounty, these projects serve as an unparalleled training ground for the next generation of scientists and engineers. A graduate student working on the Euclid mission isn't just writing a thesis. They are learning to manage colossal datasets, write complex simulation code, and collaborate with a diverse international team. They are developing skills in high-performance computing, advanced statistics, and systems engineering that are in high demand across numerous industries, from finance to artificial intelligence. This cultivation of STEM talent is a critical long-term investment for any nation's economic and intellectual capital. Furthermore, these endeavors satisfy a profound and deeply human need for exploration and meaning. Since the first humans looked up at the night sky, we have been driven to understand what we see there. This quest is a fundamental part of our culture, our philosophy, and our identity. Funding dark energy research is, in a very real sense, funding a modern-day version of building cathedrals or launching great voyages of discovery. It is an investment in inspiration, in wonder, and in answering the most basic questions a thinking species can ask. Where did we come from? What is this place, and what will become of us? The images and discoveries that flow from these missions capture the public imagination, inspire children to dream of becoming scientists, and remind us all of what we can achieve when we work together toward a grand, shared goal. Of course, this investment is not without its critics, and their concerns about opportunity cost deserve a thoughtful hearing. The argument is straightforward. Every dollar spent on a space telescope is a dollar that could have been spent on alleviating immediate human suffering, funding medical research, or developing clean energy solutions. This is a powerful moral and practical dilemma. Proponents counter that the budgets for these scientific projects are a minuscule fraction of overall government spending, often compared to the cost of a single military aircraft or a few miles of highway, and that a society must be able to walk and chew gum at the same time, addressing urgent earthly problems while also investing in long-term knowledge and inspiration. They also point out that the line between pure and applied science is often blurry. No one could have predicted that studying the physics of atoms would lead to the semiconductor revolution and the digital age. Similarly, the tools we build to decode dark energy may one day unlock technologies we cannot yet even conceive. Ultimately, the enterprise reflects a calculated gamble on the value of knowledge itself, a belief that understanding the fundamental rules of the universe is not a luxury, but a necessity for a species with a future as long and ambitious as its past. This global commitment, with all its costs and complexities, stands as a powerful signal that the mystery of dark energy is not just an academic curiosity, but a priority for humanity itself, a challenge we have chosen to meet with our full collective ingenuity and resolve. While the cosmological constant and quintessence represent our leading frameworks, the very nature of scientific discovery demands we look beyond the horizon to ideas so radical they could rewrite the rules of the cosmos entirely. One of the most unsettling possibilities is that of phantom dark energy, a scenario where the equation of state parameter W is not just slightly different from -1, but is actually less than -1. This isn't a minor tweak, it's a descent into a truly bizarre realm of physics. If dark energy has W less than -1, its energy density doesn't remain constant as the universe expands, it actually increases. This creates a terrifyingly unstable feedback loop. As the universe grows, phantom energy becomes more powerful, which causes the expansion to accelerate even faster, which creates more space and thus more phantom energy, on and on in a runaway cycle of self-destruction. This leads to a cosmological doomsday scenario known as the Big Rip. In this fate, the accelerating expansion doesn't just push galaxies apart. It eventually becomes so powerful that it overcomes all the forces holding structures together. First, galaxy clusters are torn apart, then individual galaxies. As the phantom energy intensifies, it rips apart solar systems, then planets, then stars. In the final fraction of a second cataclysm, the repulsive force would exceed the very bonds holding atoms and atomic nuclei together, shredding the fabric of spacetime itself and dissolving all matter into its most fundamental components. It's a hypothesis that pushes our understanding of physics to its absolute limit, as such behavior challenges fundamental energy conditions, but it remains a mathematically possible, if frightening, outcome that future observations could either rule out or terrifyingly confirm. Another fascinating avenue of research moves away from treating dark energy and dark matter as completely separate, non-interacting entities. What if they talk to each other? This is the premise of coupled dark energy-dark matter models. In our standard picture, these two dark components only influence each other through their gravitational effects on the overall expansion of the universe. But theorists are exploring the possibility of a direct, non-gravitational interaction between them. Imagine if dark energy could slowly decay into dark matter, or vice versa. Or perhaps there's a new fifth force that acts exclusively between these dark sectors. This kind of coupling could offer elegant solutions to several nagging problems. For instance, the "why now" problem, the coincidental timing where dark energy becomes dominant just as complex life arises, might be explained if this interaction naturally triggers the onset of acceleration at a specific point in cosmic history. The interaction would also leave a distinct imprint on how cosmic structures form. A coupling that transfers energy from dark matter to dark energy would suppress the growth of galaxies and clusters in a unique way, different from the suppression caused by a simple cosmological constant. This creates a specific, testable fingerprint that next-generation telescopes like Euclid and the Rubin Observatory will be hunting for. Finding evidence for such a conversation in the dark sector would be a monumental discovery, revealing a hidden layer of complexity in the laws of physics and forging a tangible link between the two greatest mysteries of the cosmos. Perhaps the most profound shift in thinking comes from theories that attempt to unify quantum mechanics with gravity. Our current dilemma stems from the fact that we're applying Einstein's theory of general relativity, which describes gravity on large scales, to the entire universe, while simultaneously using quantum field theory, which describes the physics of the very small, to calculate the vacuum energy. These two frameworks are famously incompatible at their extremes. Loop quantum cosmology is one ambitious attempt to resolve this by applying the principles of loop quantum gravity, a leading candidate for a theory of quantum gravity, to the universe as a whole. In this approach, the smooth continuum of spacetime described by Einstein is replaced by a fabric woven from tiny, discrete loops at the smallest possible scale, the Planck scale. This granularity of space itself acts as a natural regulator, preventing the quantum vacuum energy from reaching those absurdly high values that cause the cosmological constant problem. Even more intriguingly, some versions of loop quantum cosmology naturally predict a phase of late-time acceleration that looks very much like dark energy, but without needing to invoke any new ad hoc fields or constants. It emerges directly from the quantum geometry of spacetime. This suggests that dark energy might not be a substance or a field at all, but rather a signal that we are finally seeing the quantum structure of gravity itself imprinted on the largest scales of the cosmos. The constant churn of these new ideas is not a sign of weakness in cosmology. It is its greatest strength. It demonstrates a field alive with creative ferment, where researchers are willing to question even their most fundamental assumptions in the pursuit of truth. The standard lambda CDM model is phenomenally successful, but its reliance on two completely unexplained dark components is a clear sign that it is likely an effective theory, a tremendously good approximation that nonetheless hides a deeper, more complete reality. The next breakthrough won't necessarily come from a more precise measurement of W. It could come from a completely unexpected corner. It might be a strange anomaly in the gravitational wave signal from a merging black hole, a bizarre feature in the high-energy neutrinos detected from a distant blazar, or a statistical glitch in the distribution of galaxies that simply doesn't fit the standard model's predictions. This is what makes the search so electrifying. We are not just fine-tuning a known model. We are explorers waiting for the universe to reveal its next great surprise, a clue that will guide us toward a revolution in physics as profound as those initiated by Newton and Einstein. The journey to decode dark energy is far from a straightforward path to an answer. It is a sprawling, dynamic, and unpredictable adventure into the unknown, and the most exciting chapters are undoubtedly still to be written. But behind every cosmic data point and every elegant equation, there are people. The story of dark energy isn't just a tale of telescopes and theories. It's a profoundly human drama, a saga of late nights, stubborn persistence, and the electrifying thrill of seeing something in the universe that no one has ever seen before. Consider the two teams racing for the same discovery in the 1990s. Saul Perlmutter, leading the supernova cosmology project out of Berkeley, was a physicist by training, bringing a methodical, systematic approach to the problem. He describes the effort as building a supernova assembly line, a meticulous process of scanning the sky, taking images, and then comparing them weeks later to find the telltale new pinpricks of light. It was grueling, painstaking work, and the initial results were confusing, refusing to conform to the expected model of a universe slowing down. Perlmutter's team was the first to see the signal, but they were also the most cautious, spending months trying to kill their own result, convinced they must be making a mistake. On the other side of the Pacific, the High-Z supernova search team, led by Brian Schmidt, and with Adam Rees doing much of the crucial analysis, was taking a slightly different tack. This group was dominated by astronomers, and their approach was a bit more instinctual. Brian Schmidt has spoken vividly about the moment the truth became inescapable. He recalls running the analysis in late 1997 and getting a result that was, in his own words, downright bananas. The universe was not just expanding, it was speeding up. His first reaction wasn't joy, but absolute terror. He spent the next 2 weeks in a state of panic, desperately trying to find the error, the bug in the code, the overlooked source of dust, anything that could explain away this seemingly nonsensical result. He was a young scientist, and he was terrified of being the one to go out on a limb and claim something that would turn out to be an embarrassing mistake. Meanwhile, Adam Rees, then a postdoctoral fellow, was deep in the data. He was the one who developed a key method to account for the dimming effects of interstellar dust, a potential fatal confounding factor. When he applied his corrections and the acceleration signal not only remained but grew stronger, he knew they were onto something world-changing. He sent an email to Brian Schmidt with the now famous subject line, "Please do not share this with anyone, and you may want to sit down for what I am about to tell you." The attached graph showed the data points screaming away from the prediction of a decelerating universe. It was the moment of terrified, exhilarating clarity. Both teams, working independently and competitively, had been dragged kicking and screaming to the same unbelievable conclusion. Their decision to announce their findings jointly at a conference in 1998 is a powerful testament to the scientific spirit, a fierce rivalry ultimately superseded by a shared respect for the data and a collective responsibility to a truth larger than any individual. The human element didn't end with that Nobel Prize-winning discovery. Today, a new generation of scientists is leading the charge, embodying the same mix of passion and perseverance. Scientists like Ofer Lahav at University College London, who has been a guiding force for decades in large-scale surveys, helping to coordinate the global effort to go from merely detecting dark energy to precisely measuring its properties. Or Chihui Chang at the University of Chicago, an expert in weak gravitational lensing who works on the painstaking task of extracting a clear signal from the incredible noise and systematic errors, a process she likens to hearing a whisper in a hurricane. Then there's Dylan Brout at Boston University, who is using the latest supernova data to probe the Hubble Tension, the stubborn discrepancy in the expansion rate that might be the next great clue. These researchers aren't mythical figures in lab coats. They are people who spend their days writing code, debugging software, teaching students, and worrying about funding proposals. They experience the same frustrations and moments of doubt as anyone else. What unites them all, from the Nobel laureates to the graduate students just starting out, is a quality that can't be measured by any equation, a deep and abiding sense of wonder. It's the driving force behind the years of tedious work, the willingness to question everything, and the courage to follow the evidence no matter how strange the path becomes. Brian Schmidt has said that as a child, he would lie on his back in the Australian outback, looking up at the magnificent spectacle of the Milky Way, and feel a profound curiosity about how it all worked. That childhood wonder never left him. It simply became the engine for a lifetime of inquiry. This is the true heart of the scientific endeavor. It is not a cold, robotic process of collecting facts. It is a deeply human journey of curiosity, collaboration, and occasional bewilderment, driven by the desire to understand the magnificent universe we find ourselves in. Every plot point on a graph, every line of code in a simulation, every minute of telescope time is ultimately a reflection of that shared human wonder. And the best part is, you don't need a PhD or access to $1 million telescope to be a part of this incredible journey. The quest to decode dark energy is one of the most collaborative efforts in the history of science, and there are more ways than ever for you to roll up your sleeves and contribute directly to real cosmological research. Imagine, from the comfort of your own home, you could help astronomers classify distant galaxies, their shapes subtly distorted by the very dark matter we're trying to map. This isn't science fiction, it's the power of citizen science, and it's happening right now on platforms like Zooniverse. This online portal is a gateway to genuine discovery, where researchers upload massive datasets that are too vast for any small team to analyze alone. You could be presented with an image from a deep space survey and asked to trace the shape of a galaxy, your human pattern recognition skills helping to train algorithms or even spotting anomalies that a computer might miss. Every classification is a tiny but vital piece of the puzzle, and thousands of volunteers together create a statistical power that is indispensable to modern cosmology. You're not just playing a game, you're actively contributing to the same type of data that constrains the properties of dark energy, turning your curiosity into a tangible force for scientific progress. Staying on the cutting edge of these discoveries has never been easier, thanks to the incredible transparency of modern space agencies. You can become a virtual mission controller for the Euclid Space Telescope or the James Webb Space Telescope by simply following their social media channels and official websites. The European Space Agency and NASA regularly release raw, breathtaking images almost as soon as they beam back to Earth, along with detailed blogs written by the scientists and engineers explaining what they're seeing and why it matters. You can watch launch live streams, attend virtual public conferences, and read press releases that break down complex findings into accessible language. By following these missions, you're not just a passive observer, you're bearing witness to history as it unfolds, sharing in the anticipation of each new data release and the thrill of a potential breakthrough. This direct line to the science creates a global community of space enthusiasts, all learning and speculating together in real time. For those who want to dive even deeper, a wealth of resources awaits to satisfy your curiosity. If you prefer the narrative sweep of a documentary, films like The Dark Universe episode of Nova or the visually stunning Journey to the Edge of the Universe provide breathtaking context. For a more structured understanding, online learning platforms like Coursera and edX offer courses from leading universities on cosmology and astrophysics, often taught by the very researchers leading the charge. And if you're ready to truly geek out, there are brilliant books that make these complex ideas accessible, such as The Accelerating Universe by Mario Livio, which delves into the beauty and mystery of cosmic expansion, or Brian Greene's The Fabric of the Cosmos, which explores the nature of space and time. For the hands-on learner, software like the free Universe Sandbox allows you to create your own virtual cosmos, tweaking the strength of dark energy to see firsthand how it would alter the fate of galaxies over billions of years. These tools transform abstract concepts into intuitive, interactive experiences, allowing you to develop a deeper, more personal understanding of the forces shaping our universe. Your engagement, in whatever form it takes, is more valuable than you might realize. Every time you watch a video, read an article, or participate in a citizen science project, you are casting a vote for curiosity. You are demonstrating that there is a passionate, global audience for fundamental science, which in turn helps justify the continued funding for these ambitious and expensive missions. But beyond that, you are joining a conversation that stretches back to the first humans who looked up at the starry sky and wondered what it all meant. You are becoming part of a story that is still being written, a collective effort to push the boundaries of human knowledge. So the next time you look up at the night sky, remember that you don't have to just wonder. You can explore, you can learn, you can contribute, and you can be an active participant in the greatest detective story there ever was. So here we are at the edge of the known universe, staring into a mystery that makes up nearly 70% of everything. We've journeyed from Einstein's reluctant fudge factor to the Nobel Prize-winning shock of accelerating supernova. We've seen how the ghostly imprint of ancient sound waves and the subtle warping of light itself all point to the same incredible conclusion. The cosmos is not just expanding, it is flying apart faster and faster, driven by a force so mysterious we can only call it dark energy. Our best theories offer compelling candidates, from the elegant simplicity of Einstein's cosmological constant to the dynamic and evolving fields of quintessence. Yet for every answer, a deeper question emerges: the staggering fine-tuning problem, the unsettling Hubble tension, the very nature of nothingness. All of these remind us that our understanding is still provisional, a map that is still being drawn. This grand mystery is far from an academic sideshow. It is the very engine of scientific progress. It drives the creation of technology that didn't exist a decade ago, from space telescopes with billion-pixel eyes to supercomputers that can simulate universes. It forges global collaborations, uniting thousands of minds across continents in a shared pursuit of a single truth. The quest to decode dark energy is a testament to humanity's insatiable curiosity, our refusal to accept ignorance as a final answer. It shows us that science is not a static set of facts, but a living, breathing, and often messy process of discovery, filled with wrong turns, brilliant blunders, and moments of breathtaking insight that change everything we thought we knew. Ultimately, this isn't just a story about the fate of galaxies trillions of years from now. It is a story about us. It's about our place in a universe that is overwhelmingly dominated by forces we cannot see, touch, or fully comprehend. Decoding dark energy is about more than finishing a chapter in a physics textbook. It is about pushing the very limits of human knowledge, challenging our most fundamental assumptions about reality, and asking the biggest questions we are capable of asking. So the next time you find yourself under a clear night sky, look up. See it not as a static painting, but as a dynamic, evolving, and accelerating cosmos, filled with secrets we have only begun to unravel. The greatest discoveries are still ahead of us, and you have a front row seat. Stay curious, share your wonder in the comments below, and subscribe so you don't miss the next chapter in our journey to decode the